The water here is shallow, warm, and inviting. Sunlight cuts through the surface, painting shifting webs of gold across the sand, the scattered shells, and the chunks of broken coral. It is the kind of environment that feels entirely, completely safe. A place where you drop anchor, cast a net, or simply wait out to feel the ocean against your skin. You look down, and you see nothing but the seabed. And that is exactly the problem. Because right beneath the ripple of the tide, resting perfectly flush against the substrate, is an animal that has dedicated its entire evolutionary existence to erasing its own presence. It does not look like a fish. It does not even look alive. It looks like a heavy algae-stained rock or a lump of dead coral, encrusted with the debris of the ocean floor. This is a stonefish, and its survival is built on a single, uncompromising premise. If nothing knows you are there, nothing can hurt you. But if something makes a mistake of finding you, you must make absolutely sure it never makes that mistake again. Unlike the sleek, silver predators that patrol the open water, rely on explosive speed or relentless endurance, the stonefish is a creature of absolute, terrifying patience. It is heavy, compressed, and built low to the ground. Its skin is a masterpiece of deception, rough and warty, naturally colored to mimic the exact shades of mud, sand, and dead reef. But it goes further than mere coloration. The stonefish secretes a sticky mucus that traps fine grains of sand, microalgae, and tiny particles of marine debris, effectively wearing the ocean floor like a tailored suit. It settles into the sediment, flaring its pectoral fins to blur the line where its body ends and the seabed begins. To a passing predator, to a wandering crab, or to a human eye scanning the shallows, there is simply nothing to see. And so it waits. It can sit perfectly motionless for hours, even days, conserving almost all of its energy. It doesn't stalk. It doesn't chase. It simply allows the ocean to come to it. When a small fish or crustacean drifts just a fraction of an inch too close, the illusion shatters. But only for a millisecond. The stonefish opens its massive mouth, expanding its jaws with such violent speed that it creates an instant vacuum. The prey is sucked in, swallowed whole, before the water has even had time to settle. And then, the rock goes back to being a rock. It is a brilliant, highly efficient way to hunt in environments where food can be scarce and competition is fierce. But hunting is only half of the stonefish's story. The other half, the half that has earned a reputation as one of the most feared creatures in the ocean, is how it defends itself while sitting completely exposed in shallow water. Because the stonefish cannot swim away fast enough to escape a determined predator, and because its entire hunting strategy requires it to stay exactly where it is, evolution has equipped it with a defense mechanism of pure mechanical inevitability. Running along the ridge of its back are 13 dorsal spines. They do not look like weapons. They are thick, blunt-looking, and hidden beneath the same warty, camouflage skin that covers the rest of the body. But beneath that skin, at the base of each spine, lie twin venom glands holding a chemical payload designed to inflict maximum physiological trauma. These spines are not actively wielded. The stonefish does not strike like a snake. It does not charge or ram. It is quite literally a biological landmine. The weapon is entirely pressure-activated. This design is what puts the stonefish on a direct, catastrophic collision course with humanity. We do not operate in the ocean with the sensory awareness of marine animals. We operate on assumption. We assume that if water is clear and shallow, it is safe. We work in these waters. We haul lines, we drag nets. We step out of boats to anchor them in the sand. When a fisherman is untangling a heavy net in the dark, sorting through seaweed and bycatch by touch alone, a stonefish feels exactly like a heavy piece of coral caught in the mesh. The instinctive human reaction is to grab that lump and squeeze it to pull it free. When a wader is walking through a tide pool, their foot comes down with the full weight of their body, and that is when the mechanism fires. As pressure is applied to the dorsal spines, they easily pierce through the sheet of skin covering them. These spines are engineered to be incredibly rigid, capable of punching straight through the thick rubber soles of diving booties, through leather, and deep into human flesh. As the spine penetrates, the pressure compresses the venom glands at the base. The venom is forced up through hollow ducts inside the spine, directly into the deep tissue of the victim. It is a flawless delivery system. The harder you step, the harder you grab, the deeper the spine goes and the more venom is injected. The stonefish doesn't have to decide to sting you. You sting yourself on the stonefish. The immediate aftermath of a stonefish envenomation is almost impossible to overstate. The venom is a highly complex, deeply unstable cocktail of proteins, enzymes, and neurotoxins. Its primary objective is not to kill, though it certainly can, but to generate a pain signal so overwhelming, so all-consuming, that whatever just touched the fish will instantly retreat and remember the encounter for the rest of his life. Survivors of stonefish stings often struggle to find words to describe the sensation. It is not a sting like a bee or a bite like a dog. It is an immediate, localized explosion of agony. Victims frequently report that it feels as though their foot or hand has been struck by a sledgehammer, doused in gasoline and set on fire. The pain does not peak and fade. It escalates, radiating outward from the puncture wound, traveling up the limb, consuming the entire nervous system's capacity to process sensation. This level of pain fundamentally alters human behavior in an instant. The mind panics. Fishermen drop their gear and collapse. Waders fall backward into the water, thrashing. This is where the secondary dangers of the stonefish emerge. In shallow water, a person overwhelmed by that magnitude of pain loses their ability to stand, balance, or think clearly. Drowning becomes a very real threat, not from the venom itself, but from a body's complete inability to function through the agony. While the brain is drowning in pain signals, the venom is already dismantling the tissue around the wound. It contains toxins that immediately begin breaking down muscle fibers and destroying blood vessels. The site of the puncture begins to swell rapidly, turning a sickly blue or black as tissue necrosis sets in. The skin pulls tight, hot to the touch, as massive inflammation takes hold. But the venom does not stay localized. It enters the bloodstream and the lymphatic system, traveling systematically through the body. Within minutes, victims often experience profound muscle weakness, shaking, and severe nausea. The venom attacks the cardiovascular system, causing blood pressure to plummet. Arrhythmias develop as the heart struggles to maintain a normal rhythm under the chemical assault. Breathing becomes shallow and labored. In the most severe cases, usually involving multiple spine punctures or victims with underlying health issues, this cascade of systemic failure can lead to cardiovascular collapse, respiratory paralysis, and death. Even if the victim reaches the shore, the medical nightmare is only just beginning. Because stonefish venom is incredibly dense and complex, standard painkillers like morphine often barely touch the pain. The agony can last for hours, even days, without intervention. The frontline first aid treatment for a stonefish sting is as brutal as it is simple. Heat. The affected limb must be submerged in water that is as incredibly hot as the victim can physically tolerate without suffering third-degree burns. The heat works to denature the protein-based toxins in the venom, essentially cooking the poison inside the limb to break down its molecular structure. It is a desperate, agonizing treatment, holding a swollen, dying limb in scalding water, but is often the only way to begin dialing back the sheer intensity of the pain. But the heat does not cure the mechanical damage. When a stonefish spine enters the body, it often breaks off, leaving calcified fragments buried deep inside muscle or pressed up against bone. Because the fish spends its life sitting in mud and dead coral, those spines are coated in highly aggressive marine bacteria. The puncture wound is driven deep, sealing the bacteria inside an oxygen-depleted environment filled with dying, venom-soaked tissue. It is the perfect recipe for a massive, limb-threatening secondary infection. Even with the administration of specific stonefish antivenom, which is not always available in the remote coastal areas where these encounters usually happen, the recovery is a grueling, long-term process. Surgical intervention is frequently required to cut open the wound, debride the necrotic dead flesh, and hunt down any retained spine fragments. Months later, victims often still report stiffness, nerve damage, and phantom pains in the affected limb. A single misplaced footstep can result in a lifetime of physical compromise. And yet, despite this terrifying arsenal, the stonefish is not a malicious creature. It is not an aggressor. It has absolutely no interest in humans. It does not hunt us, it does not chase us, and it certainly does not want to waste its highly metabolically expensive venom on us. If you look at the stonefish through the cold, calculating lens of evolutionary biology, its design is flawless. It lives in a high-traffic environment. The shallows are the hunting grounds for sharks, large rays, and massive predatory reef fish. If a stonefish is spotted, it cannot outswim these predators. It has to endure them. Over millions of years, the predators that attempted to eat stonefish were subjected to this exact venom. They bit down, were flooded with unspeakable pain, and either died from the cardiovascular shock or survived with a permanent, hardwired lesson: never touch the rock that bites back. The stonefish's venom didn't evolve to punish humans. It evolved to train the ocean. It enforces a perimeter of respect around an animal that refuses to move. The tragedy, the reason why stonefish injuries are so common, is that humans do not operate on evolutionary timescales. We operate on cultural ones. A shark knows intrinsically, or learns very quickly, to leave the stonefish alone. But a tourist walking on a beach in a tropical paradise does not have that instinct. A fisherman hauling a net at 2 in the morning is working against fatigue, against the rolling deck, against the darkness. They rely on their eyes to tell them what is dangerous. But the stonefish exploits the human reliance on vision. We look for the silhouette of a shark. We look for the bright, warning colors of a venomous snake or a jellyfish. We expect nature to announce its deadliest weapons. The stonefish turns that expectation against us. It weaponizes the mundane. It takes the most ordinary, harmless-looking element of the ocean, a dead, algae-covered rock, and turns it into a trigger for unbearable suffering. It exists in the exact places where human hands and human feet are most likely to go. The tide pools where children explore, the sandy flats where people play in the surf, the muddy estuaries where nets are dragged. It shares our space, completely invisible, demanding a level of situational awareness that humans are simply not built to maintain. When a fisherman grabs a heavy lump in the net, they aren't being reckless. They are just trying to do their job. When someone steps on that rock in the shallows, they aren't taking a risk. They are just trying to keep their balance. But the ocean does not care about our intentions. The stonefish does not care about accidents. The biological landmine does not differentiate between the jaws of a hunting shark and the bare heel of a human foot. It only knows pressure. And when that pressure is applied, the illusion of the safe, inviting shallows is shattered instantly, replaced by a violent reminder of the rules written long before we ever arrive at the water's edge. The stonefish requires no speed. It requires no strength. It only requires you to make a single, ordinary mistake. To understand the lionfish, you must first forget everything you know about how prey is supposed to behave in the ocean. In the hyper-competitive, deeply violent ecosystem of a tropical coral reef, survival usually dictates one of two strategies. You either blend into the background so perfectly that you disappear, or you move with such blistering speed that nothing can catch you. Everything on the reef is hiding, fleeing, or hunting. It is a world governed by frantic, nervous energy. And then there's the lionfish. It enters the visual field like a living contradiction. It does not dart. It does not seek the shadowy refuge of a coral overhang. It simply drifts. It moves through the clear, sunlit water with a slow, unhurried grace of royalty. Its massive, feathery fins spread wide in a deliberate, elegant display. Sunlight catches the translucent webbing of its fins, illuminating striking, zebra-like stripes of rust red, dark brown, and stark white. It looks less like a biological organism and more like an ornamental kite suspended in the current. It hovers above the reef, completely exposed, its large eyes tracking the chaotic movement around it while its own body remains impossibly calm. In a world where visibility usually equals death, the lionfish is a walking billboard. It is actively advertising its presence, and it can afford this extraordinary level of arrogance because its survival does not depend on swimming away from danger. Its survival is guaranteed by a defensive perimeter so unforgiving that the fish has completely traded speed for an armored chemical deterrence. Those breathtaking, flowing fins that make the lionfish so captivating to look at are an optical illusion. They are not decorative ribbons. They are a three-dimensional array of hypodermic needles. 18 rigid, venomous spines form a halo around the animal's body, arranged along the dorsal, pelvic, and anal fins. This creates a sphere of protection that makes it nearly impossible for a predator to approach from any angle without taking a mouthful of poison. The lionfish does not need to actively strike to defend itself. It doesn't coil and lunge. It doesn't hunt down threats. Its defense is entirely passive, built on the assumption of contact. If a predator makes a mistake of trying to bite it, or if a human hand reaches out to grab it, the pressure against those rigid spines pushes back the thin sheet of tissue, covering them. This mechanical action squeezes the venom glands located at the base of each spine, driving a complex cocktail of neurotoxic and inflammatory proteins straight up the groove of the needle and deep into the flesh of the attacker. It is a masterpiece of evolutionary engineering. The lionfish conserves its energy, floating like a ghost, while the anatomy does all the heavy lifting. Predators native to the lionfish's home waters of the Indo-Pacific have learned this lesson over millions of years. They recognize the bold stripes and the flared fins not as an invitation, but as a universal hazard symbol. They give the lionfish a wide berth, but this elegant balance system breaks down completely when the lionfish is removed from its evolutionary context through human interference. Specifically the aquarium trade, the lionfish was introduced into the Atlantic Ocean, the Gulf of Mexico, and the Caribbean. In these invaded waters, the lionfish is an ecological nightmare. The native prey species, small fish and vital crustaceans, do not recognize the floating red and white stripes as a threat. They have no evolutionary memory of this predator. This allows the lionfish to utilize its incredibly effective, highly specialized hunting strategy with devastating results. It uses its large, fan-like pectoral fins not just for display, but as a corral. It slowly, methodically herds small fish into confined corners of the reef. The prey, confused by the slow movement and the wide fins, simply waits. Then, in a fraction of a second, the lionfish expands its mouth, creating a powerful vacuum that sucks the prey in before it can even flinch. The lionfish can consume massive quantities of reef fish, stripping entire ecosystems bare, growing fat, and breeding at an astonishing rate because, in these new waters, absolutely nothing hunts them. Because nature cannot contain the lionfish in these invaded territories, humanity has attempted to step in. A massive, coordinated effort has emerged across coastal communities to hunt the lionfish. The goal is twofold: cull the invasive population to save the reefs, and turn this ecological disaster into a sustainable food source. On paper, the logic is flawless. The meat of a lionfish is pristine. It is a flaky, white, mild-tasting fillet that rivals the best snapper or grouper in the ocean. And crucially, the venom of a lionfish is entirely confined to the spines. It does not taint the flesh. The meat itself is perfectly safe, completely non-toxic, and highly desirable. The strategy sounds simple. Spear the fish, cut off the spines, and cook the meat. But in practice, this process introduces a terrifying new dynamic. By turning a venomous hazard into a culinary target, humans are willfully placing their hands exactly where the lionfish's defenses are designed to cause the most suffering. Underwater, the actual hunting of the lionfish is deceptively easy. Because the fish has zero instinct to flee, a diver with a spear can swim right up to it. The lionfish will simply turn its back, flaring its spines in a display of warning, fully expecting the diver to back off just like every other predator does. A quick thrust of a spear neutralizes the animal. The illusion of safety begins the moment the fish is on the spear. The diver feels victorious. The threat appears eliminated. But the most dangerous phase of the interaction has only just begun. The venom delivery system of a lionfish does not require a heartbeat. It does not require brain activity. It does not require the fish to be alive. The mechanism is entirely mechanical. This is a critical, often forgotten truth that sends hundreds of people to the hospital every year. Death does not disarm the weapon. A lionfish thrown into a cooler on a rocking boat is a loaded gun. A lionfish lying dead on a fillet table is a loaded gun. Injuries rarely happen in the water. They happen in the chaotic, confined spaces of human routine. They happen when a spearfisher is trying to slide the dead fish off the spear shaft and into a containment tube. They happen on the deck of a boat, when someone reaches into a cooler to sort a catch, their bare hand brushing against a spine hidden beneath the ice. They happen on the cutting board, when a chef or a fisherman takes a fillet knife and attempts to shear off those 18 venomous needles. All it takes is a microscopic lapse in attention. A boat rocks on a wave. A knife slips on the slimy skin. A hand reflexively reaches out to catch a sliding fish. The moment a spine punctures human skin, the penalty is instantaneous. There is no delayed onset. There is no subtle warning. The pain is explosive, often described as an electric shock, followed immediately by the sensation of a red-hot nail being driven into the bone. The venom is heavily loaded with proteins that trigger massive inflammatory pathways and target nerve endings. It is a chemical fire designed to completely overwhelm the sensory processing centers of the brain. But the venom does something else, something incredibly sinister that maximizes effectiveness. It contains compounds that cause extreme vasodilation. It forces the blood vessels around the wound to expand rapidly. This achieves two things. First, it causes localized swelling so severe and sudden that the tissue feels like it might burst, creating an intense, throbbing pressure that amplifies the pain. Second, by opening the blood vessels, the venom ensures that its toxins are swept rapidly outward from the puncture site, radiating the agony up the hand, through the wrist, and up the arm. The pain is so profound, so jarringly out of proportion to the tiny puncture wound, that it frequently induces a secondary crisis, absolute physiological panic. In the natural world, this panic is exactly what the lionfish wants. A predator struck by this pain will thrash, retreat, and flee in terror, leaving the lionfish unharmed. But on a boat, or standing ankle-deep in the surf with a fillet knife, human panic turns a painful sting into a cascading disaster. When the pain hits, the instinctive human reaction is a violent jerk. Fillet knives are dropped, sometimes slicing into legs or feet. People stumble backward, losing their footing on wet, slippery boat decks, risking concussions or broken bones. In their desperate, pain-blinded state, inexperienced handlers will sometimes grab the wounded finger and squeeze it tightly, or attempt to aggressively massage the area, mistakenly believing they can push the venom out. In reality, they are acting as a pump, forcing the neurotoxins deeper into surrounding tissue and accelerating the spread of the chemical fire. The surrounding muscles often begin to weaken and spasm. Fine motor control evaporates. The hand becomes a useless, swollen, radiating beacon of agony exactly when the victim most needs their hands to stabilize themselves or seek medical help. While fatalities from lionfish stings in healthy adults are exceptionally rare, the sheer volume of suffering is life-altering in the moment. The body's stress response kicks in, heart rate skyrocket, blood pressure spikes, and victims frequently experience extreme nausea, sweating, and hyperventilation, purely driven by the mind's inability to process the level of pain being transmitted from a single finger. Treating a lionfish envenomation requires immediate action, but it is an action that goes against basic human instinct. Ice, the universal remedy for swelling, does absolutely nothing but prolong the suffering. The venom's proteins are heat-labile, meaning they begin to break down and denature when exposed to high temperatures. The only effective first aid is to plunge the screaming, swollen limb into water that is as hot as the victim can physically bear without scalding the skin. The heat physically cooks the venom proteins, unraveling their molecular structure and slowly dialing back the intensity of the nerve signals. But this relief only comes if the treatment is applied promptly. If a fisherman decides to tough it out, assuming the pain will fade like a bee sting, they are making a terrible mistake. Without heat treatment, the venom continues its work. The throbbing agony can persist relentlessly for days. The swelling can become so severe that it restricts blood flow to the fingers, causing localized tissue damage. The joints can remain stiff, aching, and practically unusable for weeks. And because the puncture wound was delivered by a spine coated in marine bacteria, the risk of a deep tissue infection is a looming secondary threat that requires careful monitoring and antibiotics. This is the great irony of a human war against a lionfish. We looked at a creature that evolution specifically designed to be untouchable, and we decided to turn it into a commodity. We decided to eat it. Every time a human successfully cleans and eats a lionfish, it requires a delicate, high-stakes navigation around a biological boundary. The culling programs are necessary for survival of the Atlantic reefs, and the meat is undeniably delicious. But the lionfish exacts a toll for every mistake made in the process. It does not forgive a slip of the knife. It does not care if the boat hit a wave. It does not care that it has been dead in a cooler for 3 hours. The mechanism remains perfect. The chemical payload remains lethal to comfort, The lionfish is a living lesson in the duality of nature, proving that breathtaking beauty and devastating consequence are often wrapped in the exact same package. It drifts through the water, a masterpiece of form and function, hiding nothing, advertising everything. It practically begs a world to admire it, while quietly carrying the means to punish anyone foolish enough to actually touch it. It is a slow-moving, gorgeous trap. And even when we know exactly how the trap works, human confidence, routine, and a single moment of distraction are all it takes for the lionfish to prove, once again, that the reef's most beautiful display is also its most uncompromising boundary. The boundary between human control and absolute vulnerability is never thinner than on a small boat in the dead of night, out on the shallow tropical reefs. When the sun disappears, the world shrinks to a single, narrow cone of artificial light aimed down at the black water. The surface turns into a dark mirror, hiding the complex, moving machinery of the ecosystem beneath it. This is a place of heavy, repetitive labor. Nets are hauled from the depths, dripping with seawater, tangled with vegetation, and bursting with whatever the tide has offered up. Hands work blindly, driven by muscle memory and the urgent rhythm of the catch, sorting through slick, shifting shapes in the dim light. And it is exactly here, in this chaotic intersection of human routine and low visibility, that the sea snake becomes one of the most lethal organisms on the planet. The danger of the sea snake does not come from malice. It does not stalk the waters looking for a fight. The terror it represents is entirely circumstantial, born from an evolutionary masterpiece colliding with human industry. To understand the sea snake, you have to appreciate the sheer magnitude of its biological achievement. This is an animal whose ancestors walked on land, breathed air, and relied on the earth. Yet, over millions of years, it completely severed its ties to the shore, committing entirely to a life suspended in salt water. Evolution reshaped its body with ruthless efficiency. Its tail flattened out like the blade of an oar provides seamless, powerful propulsion. Specialized valves developed to hermetically seal its nostrils the moment it slips beneath the surface. Its lung extended to run nearly the entire length of its body, acting as both an oxygen reservoir and a finely tuned buoyancy control device. It even learned to cheat the rules of respiration, absorbing oxygen directly through its skin from surrounding water to extend its dives, while a specialized gland tucked beneath its tongue tirelessly filters and excretes the excess salt it swallows. It is a reptile perfectly engineered for the ocean, but these exact adaptations tether it to the shallow, sunlit margins of the sea, the coral flats, the estuaries, and the warm coastal shelves where fish are abundant and the water temperature can sustain its cold-blooded metabolism. Unfortunately, these are the exact same waters where humanity casts its nets. The collision is mathematically inevitable. The sea snake is hunting the same fish, patrolling the same reefs, riding the same tides. When a commercial net sweeps blindly through these shallow environments, it does not discriminate. The sea snake is scooped up, ripped from the weightless freedom of the ocean, and dragged up into the terrifying, crushing confinement of the mesh. If you encounter a sea snake in the open water, it is a creature of startling grace and profound indifference. They are famously docile. If given the space to maneuver, their primary instinct is to avoid conflict, utilizing their incredible agility to simply slip away into the blue. They conserve their highly metabolic venom for one thing, catching food, but a net changes everything. The moment the snake is hauled into the air, its world collapses. Gravity, a force it rarely has to combat, suddenly presses down on it. The crushing weight of the trapped fish, the abrasive nylon mesh, and the sudden exposure trigger a massive flood of stress hormones. The animal is pinned. Its escape routes are gone. The calm, exploratory hunter is instantly overwritten by millions of years of hardwired survival reflex. It twists, it coils, it tests the pressure points of its confinement. And when it finds whatever is restraining it, it bites. This is where the tragedy of human interaction begins. Fishermen, exhausted and working in the dark, misjudge the creature tangled in their gear. They rely on the assumption that snakes are aggressive, hissing, striking monsters that announce their presence. But the sea snake is none of those things. It is small-headed with relatively short fangs. It cannot strike over long distances. It bites only when something is placed directly against it. When a fisherman reaches in with bare hands to quickly yank the tangled animal free, attempting to throw it back before it causes trouble, they make the final, fatal mistake. The jerky movements, the shouting, the sudden, terrifying grip of a human hand. It all pushes a snake's stress past the breaking point. The mouth opens, the short fangs find the skin of a finger, a hand, or a wrist, and the venom is delivered. And then, the most terrifying phase of the encounter begins. Because, more often than not, the bite doesn't hurt. Unlike the agonizing, fiery explosion of a stingray barb or a lionfish spine, the bite of a sea snake is often entirely painless. It might feel like a tiny prick, a snag on a piece of wire, or the brush of a sharp scale. There is no immediate swelling, no dramatic discoloration, no screaming agony to signal that a lethal payload has just been injected. This absence of pain is the sea snake's most insidious weapon because it breeds an illusion of safety. The fisherman, feeling no distress, assumes it was a dry bite or a scratch from a fish spine. They shake it off. They go back to pulling the net. They continue to haul, sweat, and breathe heavily, their heart pumping adrenaline and blood rapidly through their body. And with every beat of their heart, they are doing the venom's work for it. Sea snake venom is a highly specialized, ruthlessly efficient cocktail optimized for one specific purpose: the immediate immobilization of fast-moving fish in an open water environment where a wounded meal could easily swim away and be lost forever. It is a profoundly powerful combination of neurotoxins, which destroy the nervous system's ability to communicate, and myotoxins, which literally dismantle muscle tissue at the cellular level. Drop for drop, it is among the most toxic substances produced by any vertebrate on Earth. While the fisherman continues to work under the artificial lights, the venom circulates quietly, slipping past the body's alarms. It takes hours for the illusion to break, and when it does, the symptoms arrive not as a sudden crisis, but as a creeping, quiet shadow. It starts as a generalized heaviness. The muscles begin to feel sore and stiff, mimicking the exact sensations of a long, grueling night of physical labor. The victim assumes they are just tired. They assume they are dehydrated. But inside their body, a catastrophic breakdown is occurring. The myotoxins are tearing apart muscle fibers. As the muscles dissolve, they release massive amounts of a protein called myoglobin into the bloodstream. The kidneys, the body's filtration system, are suddenly slammed by this toxic sludge. The urine turns a dark, horrifying shade of brown or black as the kidneys begin to clog and fail under the immense chemical load. At the same time, the neurotoxins are hunting down the neuromuscular junctions, the microscopic bridges where nerves tell muscles to move. The venom blocks these bridges perfectly. The command to move the legs is sent from the brain, but the message never arrives. Paralysis sets in, starting at the extremities and crawling steadily inward. The mind remains sharp, fully aware of the creeping numbness, fully conscious as the body betrays it. By the time the victim realizes that the stiffness isn't fatigue, the paralysis has usually reached the chest. The diaphragm, the massive muscle responsible for pulling air into the lungs, begins to falter. Breathing becomes shallow. It feels as though an invisible weight is pressing down on a rib cage. Because the onset was delayed, because the bite was painless, precious hours have been wasted. By the time the victim is struggling for breath, fighting a suffocating darkness while perfectly awake, anti-venom is often no longer effective. The damage to the kidneys and the nervous system is locked in. Without immediate, highly advanced mechanical life support, ventilators to breathe for them, dialysis machines to clean their blood, the respiratory failure is absolute. This horrifying sequence is born from panic and misunderstanding. Safe release protocols for sea snakes exist, and they rely entirely on doing the exact opposite of what human instinct demands. Experienced fishers know that speed is the enemy. When a snake is spotted in the mesh, they do not grab it. They step back. They use long tools to cut the netting or gently lower that section to gear back into the water. Water is the snake's sanctuary. The moment it is submerged, the crushing gravity is gone. The panic subsides. Its orientation returns, and its single driving instinct to escape takes over. It doesn't want revenge. It just wants to swim away. By creating distance and moving with slow, deliberate calm, the fisherman turns a deadly confrontation into a quiet disengagement. From an evolutionary standpoint, The human death caused by a sea snake is nothing more than biological collateral damage. We were never the target. The venom wasn't engineered to kill mammals. It was engineered to stop a fleeing fish in a boundless ocean. We suffer because we blindly step into a crossfire that has been raging in the reefs for millions of years. The sea snake is not a villain lurking in the depths. It is an essential predator, a regulator of the reef, keeping fish populations in check and maintaining the fragile balance of the coastal ecosystem. When we pull them from the dark water, we are pulling up a perfect reflection of the ocean's unforgiving rules. The tragedy lies in how preventable these deaths are. The sea snake doesn't hunt the boat. It is dragged aboard by a human system that refuses to acknowledge the reality of the environment it exploits. The true danger of the sea snake is not aggression. It is our own assumption that the ocean is empty, our own panic when we realize it is not, and the terrifying silent hours that follow a mistake we didn't even know we made. If you look down into the clear, sunlit shallows of a tropical coastline, the danger does not look like danger at all. It looks like a shadow. It looks like a dark, geometric-shaped wedge tightly between the rocks, or a cluster of spiky, motionless spheres scattered across the reef flat like forgotten caltrops. The water here is gentle. The light is perfect. It is the kind of environment that invites you to step out of your shoes, to wade into the surf, to reach down and touch the textures of the seafloor. And sitting right there, completely exposed, making absolutely no effort to hide, is the sea urchin. To the human eye, the sea urchin appears entirely inert. It does not possess the terrifying speed of a barracuda. It does not have the camouflage of a stonefish, nor does it wield the explosive, venomous agony of a lionfish. It does not stalk, it does not ambush, and it certainly does not flee when a shadow passes over it. It simply sits there. But this stillness is not a vulnerability. It is a strategy perfected by millions of years of evolutionary patience. The sea urchin does not need to run from you, because its survival is built on a design that turns a very act of physical contact into a prolonged, punishing lesson. The sea urchin is a creature of structural resilience. As an echinoderm, a close relative of the starfish, its body plan abandons the concept of speed entirely in favor of an impregnable radial fortress. It is a dome of armor, entirely covered in a dense, bristling forest of spines. But these spines are not simple, static spikes. They are highly complex, brittle structures made of porous calcium carbonate, and they are mounted on microscopic, highly articulated ball and socket joints. This ingenious anatomical design allows the urchin to pivot and angle its spines with surprising precision. It doesn't strike. It simply continuously reorients its defenses to face whatever is pressing against it, creating a dynamic, unyielding surface that responds to the environment purely through geometry and pressure. When a human foot steps down into the sand or a hand reaches blindly under a rocky ledge, the encounter is almost anticlimactic. There is no sudden thrashing, no aggressive bite. The urchin simply holds its ground, and as the weight of the human body presses down, the spines do exactly what they were engineered to do. They penetrate. They slide effortlessly through skin, through the rubber soles of water shoes, and deep into the soft tissue of the foot or the hand. But it is what happens next that elevates the sea urchin from a mere nuisance to a lingering medical nightmare. Unlike the rigid barb of a stingray or the hypodermic needle of a lionfish, the sea urchin's spine is not designed to stay intact. It is designed to shatter. When you instinctively jerk your hand or foot away from the sudden, sharp pain, the lateral force applied to the spine causes it to snap off below the surface of your skin. This is the core of the urchin's defensive genius. It does not deliver a venom that your body can eventually metabolize and clear. It leaves pieces of itself behind. This mechanical fracture creates a deeply persistent, slow-burning crisis that unfolds not in minutes, but over weeks and months. People constantly underestimate sea urchin injuries because they lack the dramatic, immediate horror of a venomous strike. There is no systemic shock, no plunging blood pressure, no paralysis. There is only a constellation of small, dark dots under the skin where the spines entered, accompanied by a sharp, localized ache. This visual understatement leads to the worst possible human reaction, the belief that you can simply pull it out. Equipped with tweezers, needles, and a misplaced sense of confidence, people begin digging into their own flesh to extract the fragments. But the calcium carbonate spines are incredibly fragile and highly porous. The moment you grip one with metal tweezers and apply pressure, it crumbles. It shatters into dozens of microscopic shards, turning a single puncture wound into a scattergun of debris driven even deeper into the muscle, the fat, and the connective tissue. Once those fragments are hopelessly buried, your body's immune system takes over and the true punishment begins. The immune system recognizes the calcium carbonate as a foreign invader and mounts an aggressive, relentless attack. It walls off the area, flooding the tissue with white blood cells. This triggers a cascading, localized inflammation. The entry points swell, turning an angry, painful red. And because the sea urchin spends its life slowly scraping across the bacteria-laden surfaces of the ocean floor, those spines are completely coated in a rich film of marine microbes and organic debris. The spine acts as a Trojan horse, delivering this bacterial payload deep into the tissue where oxygen is scarce and infection can thrive. Over the following days, what started as a minor prick transforms into a chronic, throbbing affliction. The area becomes hot to the touch. Walking becomes agonizing as the pressure of your own body weight pushes against the retained fragments. If a spine has snapped off near a joint, a tendon, or a ligament, a very common occurrence in hands and feet, the resulting inflammation can essentially lock the joint, causing extreme stiffness and a loss of mobility that can persist long after the initial encounter. In some cases, the body will try to isolate the indestructible calcium shards by building dense, hard nodules of scar tissue around them, known as granulomas. These hard lumps can remain under the skin indefinitely, acting as tiny, permanent reminders of the reef, flaring up with sharp pain whenever they are pressed or bumped. To truly remove them, a surgeon must go in and cut the tissue away, hunting for microscopic splinters of ocean floor embedded in the human anatomy. This slow, grueling consequence aligns perfectly with the ecology of the animal. The sea urchin does not need to kill the things that bother it. It only needs to ensure that they never try to bother it again. If a large predatory fish attempts to bite down on a sea urchin, the spines shatter inside its mouth and digestive tract. The predator doesn't die instantly, but it suffers for weeks, learning a powerful, permanent behavioral lesson. The urchin sacrifices a few replaceable spines to train the surrounding ecosystem to leave it alone. And being left alone is essential for the sea urchin to perform its critical, landscape-altering work. Beneath that dome of spines lies the underside of the urchin, and at its very center is one of the most remarkable pieces of biological machinery in the ocean, a complex, five-jawed scraping apparatus known as Aristotle's lantern. Powered by a dense network of muscles, these self-sharpening teeth are strong enough to grind down tough, leathery algae, chew through kelp stalks, and even scrape the very limestone off the coral reef itself. The sea urchin is the ultimate marine grazer. In a balanced ecosystem, it is a vital landscaper. It methodically moves across the rocks, clearing away fast-growing algae that would otherwise smother and kill the slow-growing corals. It opens up bare patches of rock where new coral larvae can settle and grow. It maintains the delicate equilibrium of the reef, preventing the environment from choking on its own vegetation. But when that balance is disrupted, the sea urchin reveals a terrifying capacity for destruction. In areas where humans have overfished or eradicated the urchin's natural predators, like sea otters, large wrasses, and specific types of starfish, the urchin population explodes. They form massive, slow-moving armies that march across the seafloor in a relentless, consuming wave. They chew through the base of towering kelp forests, cutting the giant plants loose to wash away in the tide. They strip the rocks completely bare, leaving behind a desolate, underwater desert known as an urchin barren. In these barrens, biodiversity utterly collapses. The nursery grounds for fish disappear. The hiding places for crustaceans vanish. The reef is reduced to a stark, rocky wasteland, dominated only by the shadows and spines of a million hungry urchins. It is a profound ecological paradox. The very animal that helps maintain the reef can, without the checks and balances of a healthy food web, completely dismantle it. This paradox deepens when you consider humanity's culinary obsession with the animal. Inside the armored, spiky shell of the urchin lie its gonads, known in the culinary world as uni. It is a highly prized, extraordinarily expensive delicacy, renowned for its rich, buttery texture and a complex, oceanic flavor that melts on the tongue. The global demand for uni brings humans into direct, high-volume contact with the sea urchin's defenses. Harvesting urchins cannot be done efficiently with massive nets or automated machines. It requires human hands reaching into the very environment the urchin controls. Collectors wade into the shallow reefs or dive along the rocky coastlines, working in environments that actively conspire against caution. The water surges with the tide, pushing and pulling at the diver's balance. The rocks are coated in slippery algae. Visibility shifts with the light. In this dynamic, unstable world, the collector must reach down and carefully extract a creature entirely covered in fragile, flesh-piercing needles. It is here, in the pursuit of luxury, that the vast majority of human injuries occur. A wave pushes a harvester off balance, causing to stumble and plant a hand directly onto a cluster of urchins. A diver reaching blindly into a crevice feels a sudden, sharp crunch of spines shattering against their knuckles. It is a hazard of the trade, a toll extracted by the ocean for removing one of its most heavily fortified architects. And because the injury is not immediately life-threatening, the harvesters often keep working. They ignore the dull ache in their hands, pushing to the pain to secure the catch, unknowingly allowing the inflammation to set in, the bacteria to multiply, and the fragments to settle deeper into their joints. The sea urchin does not possess malice. It is not seeking revenge for being harvested. It is completely indifferent to the culinary value of its own biology. It only knows that it must protect the soft vulnerability of its core, and it does so with absolute mechanical prejudice. When you look at a sea urchin, you are not looking at a monster. You are looking at a keystone of the coastal ecosystem, a creature that literally shapes the world it lives in. Its danger does not come from aggression, but from an uncompromising design that punishes clumsiness, assumption, and haste. It is a masterclass in passive resistance. In the shallow waters where we feel the safest, where the sand is soft and the sunlight is warm, the sea urchin waits. It does not need to chase us. It knows that eventually our curiosity, our hunger, or simply our careless footsteps will bring us to it. And when that contact happens, it will not fight us. It will simply break apart, embedding a tiny, painful piece of the ocean floor deep beneath our skin, ensuring that long after the water is dried from our feet, we will remember exactly whose territory we walked upon. The first thing that betrays the danger is how utterly, disarmingly harmless the creature looks. As it drifts through the sunlit shallows of coastal waters, hovering casually above sand flats and jagged coral rubble, it moves with the lazy, unhurried confidence of an animal that has absolutely nothing left to prove to the ocean. Its round, bulbous body bobs gently, dictated by the gentle push and pull of the tide rather than any urgent propulsion of its own. Its oversized eyes scan the vibrant, chaotic reef below, seemingly driven more by mild curiosity than by any instinctual fear. And its small, beak-like mouth is perpetually shaped into an expression that looks suspiciously, almost comically like a smile. In the high-stakes, hyper-competitive arenas of tropical lagoons and temperate shorelines, the pufferfish occupies a deeply strange ecological niche. In these waters, visibility is high, apex predators are terrifyingly abundant, and escape routes are severely limited. For almost any other creature this size and speed, swimming openly during peak daylight hours without displaying a frantic, nervous vigilance would be an immediate death sentence. Yet, the pufferfish moves openly. It does not dart. It does not hide. It does not attempt to blend into the background. This apparent boldness is not born of arrogance. It is born of chemistry. The pufferfish has adopted a biological strategy so overwhelmingly effective that it has completely reshaped the entire predator-prey dynamic that surrounds it. It allows a slow, awkward, clumsily paddling swimmer to not just survive, but to thrive in environments that would ruthlessly punish even the slightest hesitation in any other species. The pufferfish does not rely on the blistering speed of a barracuda. It does not utilize the flawless, invisible camouflage of a stonefish. It does not possess the aggressive, territorial violence of a moray eel. Instead, it relies on a molecular weapon so profoundly potent, so devastatingly absolute, that a quantity smaller than a single grain of sand can completely halt the electrical language of the human nervous system, while leaving the mind entirely awake, trapped, and fully aware of its own catastrophic shutdown. This weapon is neurotoxin, And it is not a poison that overwhelms the body through the chaotic, fiery inflammation of a stingray barb or a lionfish spine. It does not violently destroy cells or tear through tissues in a dramatic, bloody fashion. Its lethality is derived entirely from its cold, microscopic precision. To understand the horror of tetrodotoxin, you have to look at the very foundation of how a living body operates. At the cellular level, your nerve cells communicate with your muscles, your heart, and your lungs through highly controlled, rhythmic electrical signals. These signals travel along the membranes of your nerves by allowing sodium ions to flow in and out through specialized microscopic channels. You can think of these channels as tiny mechanical gates that open and close in exact, rapid-fire patterns. Every movement you make, every sensation you feel, every breath you draw, and every beat of your heart is a result of these microscopic gates translating chemical gradients into action. Tetrodotoxin is a molecule shaped by evolutionary perfection to do exactly one thing. It fits into those sodium channels like a perfectly cut key slipping into a lock. And once it is inside, it jams the gate permanently shut. It prevents the sodium ions from entering the nerve cell. The electrical signal is immediately stopped in its tracks. It cannot propagate. It cannot jump the gap. The command from the brain is sent, but the message never arrives. Muscles do not contract, not because they are damaged, but because the biological wire connecting them to the brain has been severed at the molecular level. This mechanism is what makes tetrodotoxin uniquely, unspeakably terrifying from a physiological perspective. Many neurotoxins found in the natural world will cause massive confusion, delirium, or merciful loss of consciousness very early in the exposure. But tetrodotoxin does not cross the blood-brain barrier easily. The poison isolates the brain, leaving the mind entirely intact, completely lucid, while systematically stripping the body of its ability to respond to the world. For a human victim, the progression of this poisoning is a slow, waking nightmare. It almost always begins with a strange, subtle tingling around the lips, the tongue, and the fingertips. It is a light, almost vibrating sensation. It is not painful, and because of that, it is deeply deceptive. That tingling is the early warning siren that nerve transmission is beginning to fail. Soon, the tingling gives way to a profound numbness that spreads steadily across the face and down the limbs. The victim attempts to stand or to move their arms and experiences a muscle weakness that feels like crushing, heavy exhaustion rather than pain. A creeping, leaden heaviness settles into the bones, making the simple act of lifting the head feel like an impossible athletic feat. As the paralysis deepens and the sodium channel slams shut across the body, the victim's ability to speak disappears. The vocal cords slacken. The tongue becomes a useless weight in the mouth. Then the ability to swallow evaporates. Saliva pools, creating a terrifying choking sensation. And finally, the paralysis reaches the chest. The diaphragm, the massive sheet of muscle that pulls air into the lungs, begins to weaken, stutter, and ultimately fall silent. All the while, consciousness remains perfectly, agonizingly clear. The victim is fully capable of perceiving the rising panic in the room, fully capable of hearing the voices of those trying to help, fully aware of the suffocation taking hold, and completely aware of the progressive, total loss of their bodily control. The lungs themselves are perfectly healthy. They are not damaged. They simply can no longer receive the electrical instructions required to expand. The body is transformed into a fully aware prison that can neither move, nor flinch, nor cry out for help. The pufferfish, in a bizarre twist of biology, does not even manufacture this doomsday molecule on its own. This is a critical detail that is often wildly misunderstood, even by the people who risk their lives to consume it. The toxin does not come from the fish's DNA. It originates from symbiotic bacteria, living deep within the fish's tissues. These microscopic organisms, belonging to several bacterial genera, including Vibrio and Pseudomonas, produce tetrodotoxin as a natural metabolic byproduct. The pufferfish accumulates these bacteria and their deadly exhaust through its diet and through natural microbial colonization, drawing the poison from the environment and storing it inside its own body, rather than synthesizing it internally. The toxin concentrates most heavily in the liver, the ovaries, the intestines, and the skin of the fish. This symbiotic relationship transforms a pufferfish into a highly mobile, unpredictable reservoir of poison. And because the toxin is accumulated from the environment, The toxicity of any given pufferfish can vary wildly depending on its specific habitat, its recent diet, the season of the year, and its individual health. It is fundamentally impossible to determine the safety or the toxicity of a pufferfish through appearance alone. Two pufferfish of the exact same species, caught on the exact same day, on the exact same stretch of reef, can differ so drastically in their toxin concentrations that one might cause a mild stomachache, while the other holds enough poison to kill 30 adult humans. From an ecological standpoint, this borrowed chemical defense reshapes interactions far beyond anything a human will ever experience. In the wild, predators that attempt to consume a pufferfish learn a very fast, very permanent lesson through fatal trial and error. The predator bites down, the toxin is absorbed, and the predator dies. Over evolutionary time, the surviving predators learn to associate the distinct shape, the slow movement, and the often bright patterns of the pufferfish with absolute consequence. The fish's apparent vulnerabilities, its lack of speed, its bright coloration, its clumsy swimming, are actually highly evolved signals. They are advertising danger rather than trying to hide from it. Because the pufferfish does not need to invest massive amounts of metabolic energy into building powerful swimming muscles or developing complex escape mechanics. It can allocate all of that saved energy into growth and massive egg production. But what about the iconic behavior that gives the fish its name, the inflation? For decades, popular culture has misunderstood the puffing mechanism as the animal's primary defense. In reality, the inflation is entirely secondary to the tetrodotoxin, serving a much more immediate mechanical function. When a pufferfish is actively threatened, cornered, or harassed, it rapidly gulps massive amount of water or air if it is pulled to the surface. It forces this fluid into a highly elastic, specialized stomach, expanding its body to several times its normal size in a matter of seconds. It transforms from a small, bite-sized fish into a rigid, highly pressurized sphere, often covered in sharp, outward-facing spines that lay flat when the fish is relaxed. This mechanical transformation makes it physically difficult, or even geometrically impossible, for a predator to fit the fish inside its mouth or swallow it. The inflation buys time. It does not guarantee safety, because inflation alone will not stop a large, determined predator with a wide enough jaw from simply biting down and inflicting fatal crushing damage. But when that mechanical defense is combined with the incredibly toxic tissues, it creates an inescapable lethal trap. Even partial ingestion, or a mere bite that breaks the skin of the pufferfish, can be fatal to the attacker. Tetrodotoxin does not require digestion in the stomach to enter the predator's bloodstream. It can be absorbed rapidly through the mucous membranes of the mouth and through fresh wounds almost immediately upon contact. Nature learned its lesson. The predators of the reef leave the smiling, floating balloon alone. Humans, however, represent an entirely different category of predator. We are a predator that does not lure avoidance through slow, evolutionary timescales, but through culture, ego, myth, and sometimes profound tragedy. In several countries, but most famously and intricately in Japan, the pufferfish has been dragged out of the water and transformed from a glowing ecological warning sign into the ultimate culinary challenge. In this culture, the danger of the animal is not a deterrent. The danger is the entire point of the appeal. Known as fugu, pufferfish meat is considered a pinnacle of luxury dining. It is consumed in paper-thin slices, arranged on plates with breathtaking artistic precision, almost always served raw or only lightly cooked. It is sold with the solemn promise that proper, masterful preparation removes the poison while preserving the transcendent experience of the meal. This belief, while culturally powerful, terrifyingly oversimplifies both the resilient biology of tetrodotoxin and the flawless execution required to manage it. The narrative implies that the poison can be tamed. It cannot. The toxin is not evenly distributed throughout the fish. It is not predictable. And most importantly, it is not neutralized by any technique known to the culinary arts. Cooking the fish does absolutely nothing to make it safer. Tetrodotoxin is an incredibly heat-stable molecule. It remains perfectly intact, its molecular key completely undamaged, at temperatures that far exceed those used in boiling, frying, or baking food. Freezing the fish preserves the toxin perfectly. No chemical marinade, no acid, no amount of salt can break the poison down, meaning that the safety of the diner depends entirely 100% on the physical, surgical removal of all toxic organs and tissues without allowing even a microscopic drop of contamination to touch the edible, white flesh. The margin for error in this process is vanishingly, terrifyingly small. We are not talking about avoiding a poison gland that will make you sick. We are talking about a substance where the difference between a harmless, expensive appetizer and a lethal, suffocating dose is measured in micrograms. The scale of the danger is so incredibly fine that if a chef's knife blade accidentally grazes the liver or the ovaries, and then makes a slice into the edible muscle, that imperceptible trace contamination left on the steel is enough to kill the person who eats it. Licensed fugu chefs are not merely cooks. They undergo years of grueling, highly regulated training. They must pass rigorous written and practical tests to prove they have memorized the exact, intricate anatomy of the fish, the precise location of every toxin-rich organ, and the flawless knife techniques required to isolate and extract the edible muscle without a single rupture or spread of the poison. And yet, even with this extreme level of institutional training, deaths still occur. They occur because human error, no matter how disciplined practitioner, can never be fully eliminated, and they occur because nature is inherently variable. Sometimes the toxin levels in specific fish are so uncharacteristically high, or have migrated into muscle tissue in ways that defy standard anatomy, that even a perfectly executed cut is not enough. When dealing with a compound that absolutely does not forgive a mistake, perfection is an impossible standard to maintain forever. But the danger skyrockets when the pufferfish leave the hands of the masters. Amateur preparation, whether by untrained home cooks trying to save money or by adventurous tourists seeking a thrill in unregulated coastal markets, dramatically increases the body count. No amount of careful visual inspection, no confident taste testing, and no amount of bravado can reveal the presence of tetrodotoxin. Once it has entered the food, you cannot see it, you cannot smell it, you cannot taste it. Tourism culture massively amplifies this danger by reframing life-threatening risk as a marker of authenticity. It encourages travelers to seek out underground or unregulated experiences that involve consuming foods known to be dangerous, operating under the deeply flawed psychological assumption that survival itself is proof of cultural immersion and bravery. This narrative ignores the cold, hard biological reality of the poison. Tetrodotoxin does not care about your bravery. It does not respect culinary tradition. It does not honor your intent. And the fish itself does not distinguish between a sacred, ceremonial preparation by a master chef and the reckless, clumsy handling of a thrill seeker. In some regions, illegal preparation persists specifically because there is a demand from diners who actively want to be poisoned just a little bit. They request that the chef leave the faintest trace of the toxin on the meat, believing that consuming microscopic amount of the poison produces a pleasant, euphoric, tingling sensation on the lips and tongue without lethal consequences. This is the ultimate hubris. That sensation, often described as a mild, exciting numbness, is not a controlled, recreational effect. It is the literal, physiological onset of stage 1 neurotoxic exposure. That tingling is a feeling of the first wave of your sodium channels being permanently locked shut. Its presence indicates that the toxin has already successfully entered the bloodstream and has begun actively interfering with your nervous system. At the exact moment a diner feels that thrill, the difference between a pleasant numbness and total respiratory failure is no longer under their conscious control. They have rolled the dice, and they simply have to wait to see how much poison was actually on the blade. From an evolutionary perspective, the irony of the human relationship with the pufferfish is stark and deeply humbling. Tetrodotoxin evolved over millions of years as a deterrent precisely because it is merciless, perfectly reliable, and completely indifferent to dosage miscalculations made by the creatures that try to eat it. It is not a poison designed to teach a predator moderation. It is not designed to allow a shark to survive after sampling a small bite. It is designed to impose absolute, final consequences. It shapes the behavior of the ecosystem through elimination rather than negotiation. Humans, by attempting to tame this ancient toxin to the lens of culinary tradition, are engaging in a cultural gamble against a molecular system that has remained unchanged for millions of years. The selective pressures of the ocean created tetrodotoxin to favor stability, not adaptability to human desires. What makes the pufferfish particularly unsettling is not just that it carries this doomsday weapon, but that it does so while appearing so incredibly approachable, so charming, and so benign. It occupies the shallow, sun-warmed waters frequented by swimmers, snorkelers, and casual fishers who look down at its rounded form and see a cartoon character, entirely failing to recognize the invisible threat drifting just beneath the surface. Handling a pufferfish, even if you have absolutely no intention of eating it, can be a hazardous undertaking because the tetrodotoxin is heavily concentrated in the mucus and the skin. Simply holding the fish with bare hands can expose a person to the poison. If you have a small cut on your finger, or if you accidentally rub your eyes or your mouth after touching the animal's skin, the toxin can enter the bloodstream, bypassing the digestive system entirely. It makes improper handling risky in ways that are never immediately obvious to someone who just wanted to hold a funny, puffing fish. In this sense, the pufferfish represents one of the ocean's most profound and terrifying ecological lessons. It shows us how evolution often hides its most effective, most devastating weapons behind misleading signals, actively exploiting the assumptions of predators rather than confronting them with sharp teeth or aggressive posturing. Seen within the context of its vibrant, violent ecosystem, the pufferfish is not a monster. It is a masterpiece of biochemical adaptation. It is a living, breathing demonstration that survival in the wild does not always favor the strongest, the largest, or the fastest. Sometimes survival favors absolute precision and cold inevitability. Tetrodotoxin allows the pufferfish to occupy exposed, beautiful niches, to reproduce successfully, and to deter the most fearsome predators in the ocean without ever having to be constantly vigilant. It shapes entire reef communities simply by existing, removing any predator foolish enough to test it from the system entirely. For humans, the true danger lies not in encountering the pufferfish itself, but in our persistent, arrogant misunderstanding of the nature of its defense. We believe that our traditions, our knife skills, or our bravery can somehow override a molecule whose sole evolutionary purpose is to end encounters decisively and permanently. The pufferfish does not challenge you to test your limits. It does not care about your courage. It simply exists, drifting lazily through the shallows, carrying a microscopic key that will lock the gates of your nervous system, shutting down your body while leaving your mind wide awake in the dark. It is the ultimate reminder that in the ocean, some things are only cute right up until the exact moment they stop your breathing. The coastline is a borderland. It is a restless, shifting margin where the ocean continuously negotiates its boundaries with the earth, claiming and surrendering territory hour by hour in rhythm with the moon. In this dynamic space, we find the tide pools, the mangrove roots, the rocky intertidal zones, and the shallow, sun-warmed mudflats. For humans, this environment feels uniquely accessible. It feels playful. It is a place where families wander barefoot, where children flip over stones out of sheer curiosity, and where the ocean seems to have been conveniently miniaturized for our entertainment. It is a place where food appears to be lying around, waiting to be scooped up rather than hunted. And in this deceptively safe borderland, we encounter the crab. To the casual observer, the crab does not inspire fear. It does not possess the sleek, ominous silhouette of a shark, nor the hidden, chemical malice of a venomous spine. It scuttles sideways with frantic, almost awkward speed. It waves its claws in the air in a manner that looks far more theatrical and comical than genuinely threatening. We have anthropomorphized them into cartoons, treating them as the ocean's quirky, harmless bottom dwellers. That familiarity, that persistent cultural assumption of harmlessness, is precisely the problem. Because crabs are not simple, panicking creatures operating on blind reflex. They are heavily armored biomechanical tanks equipped with some of the most ruthlessly efficient, mechanically devastating crushing tools in the entire marine world. They've been refined by hundreds of millions of years of evolutionary pressure to do one specific thing with absolute perfection: to break armor, to dismember prey, and hold fast no matter how violently the world tries to pull them away. To understand the danger of a crab, you must stop looking at its claw as a hand or a pincer or a tool for grabbing. You must look at it for what it truly is: a biological hydraulic press engineered to apply catastrophic force over microscopic surface area. The anatomy of a crab's claw is a marvel of leverage and structural integrity. Unlike human limbs, where the soft muscle sits on the outside of the bone. A crab's muscles are packed tightly inside a rigid, unyielding exoskeleton made of chitin and calcium carbonate. This creates a closed, highly pressurized system. Thick bundles of striated muscle are anchored directly to the interior walls of the shell. When the crab commands those muscles to contract, the force is translated through a series of specialized, jointed segments that act as incredibly efficient fulcrums. The energy is multiplied, focused, and driven into the cutting edge of the claw with terrifying speed. In many species, the danger is compounded by a stark, asymmetrical design. The crab does not carry two identical weapons. It carries a specialized arsenal. One claw is typically the cutter, thinner, sharper, lined with serrations designed to slice through soft tissue, tear meat from bone, and manipulate food with surprising dexterity. The other claw is the crusher. This claw is massively enlarged, heavy and blunt, lined with thick, rounded molar-like teeth. Its sole evolutionary purpose is to obliterate hard shells. This asymmetry means that the danger a crab poses is highly situational, entirely dependent on which weapon it deploys and where it lands. And when one of those weapons closes on human flesh, the mechanical reality of the situation overwhelmingly favors the crab. Human skin, our fingernails, and the delicate tendons that run close to the surface of our hands are incredibly soft relative to the calcified structures that crabs have evolved to destroy. The crab's evolutionary diet consists of snails, clams, oysters, and other crustaceans, animals protected by solid, rocky armor. Crushing those shells requires immense, sustained force. When you place a human finger into a mechanism designed to crack open an oyster, the result is exactly what physics dictates. A crab does not pinch. It crushes. Fingernails can easily crack, splinter, or split completely down the middle under the pressure of a crusher claw. It is not because the crab is acting out of malice or unnatural aggression. It is simply because the compressive force applied to the nail far exceeds the tensile strength of human keratin. But the initial crush is rarely the end of the encounter, because a human reaction's sudden pain instantly triggers the crab's most formidable defensive behavior: grip persistence. In the wild, crabs are constantly preyed upon by birds, large fish, octopuses, and mammals. These predators attempt to pry them off rocks, drag them out of crevices, or shake them aggressively to break their limbs. Because of this, the crab's instinctual response to being grabbed or pulled is never to let go. Releasing its grip is not part of its defensive vocabulary. When a crab feels resistance, when it feels it is being pulled away, its nervous system fires a command to clamp down exponentially harder. When a human reaches into a tide pool and grabs a crab, or when a crab clamps onto a wandering finger, the human instinct is to immediately and forcefully yank the hand away. To the crab, this sudden upward pull is the exact signature of a predator trying to kill it. The claw locks. The muscles bear down. In that frantic moment of panic, the human continues to pull, turning what was originally a crushing injury into a severe tearing injury. The serrated edges of the claw drag across the skin, ripping through the epidermis and digging into the tissue below. The tendons and the fingers, stretched tight by the pulling motion, are deeply bruised or even lacerated by the relentless pressure. The human and the crab enter a desperate mechanical stalemate, and because the crab's claw is driven by muscles that do not easily fatigue under static load, the crab is structurally built to win that waiting game. This danger is radically amplified by the environment in which these encounters usually take place. In the intertidal zone, as the tide pulls back and the water drains away, crabs are left highly vulnerable. The rocks begin to bake in the sun. The pools of water shrink. This environment concentrates interactions, forcing these armored animals into tight, confined spaces where their escape routes are entirely cut off. A crab wedged deep beneath a rock or tucked tightly into a narrow, dark crevice cannot run away. It cannot scuttle sideways to safety. So, it prepares to fight with the only tool it has. When a human hand reaches blindly into that crevice, perhaps looking for a dropped pair of sunglasses or just exploring the textures of the reef, the encounter happens at point-blank range, with absolutely zero warning and no room for either party to maneuver. The resulting injury feels sudden, shocking, and deeply unfair to the victim. But it is not because the crab moved with blinding speed. It is because the human grossly underestimated what was already waiting in the dark. And the crab is not a passive participant while it holds on. It is a highly active spatial fighter. If a crab grips a finger while it is still partially wedged inside a rock formation, it will twist its armored body and brace its legs against the stone walls of crevice. It uses the surrounding environment to anchor itself, gaining massive mechanical leverage. This allows the crab to amplify the crushing force of its claw without having to expend any additional muscular effort. It pits the strength of the unyielding rock against the soft tissue of the human hand. This level of environmental awareness is driven by a sensory system that humans frequently fail to recognize. Crabs do not rely solely on their stalked eyes to see you coming. Their bodies and legs are covered in microscopic, highly sensitive setae, tiny bristles that detect the faintest vibrations traveling to the water and the substrate. They can feel the pressure waves of approaching footsteps. They can sense the shifting of loose rocks. They can feel the displacement of water as a hand reaches into their pool. In the intertidal zones, this sensitivity means a crab knows you are there long before you ever make visual contact. By the time your fingertips brush against its shell, the crab is already hyperalert. Its muscles tense, its claws raised and primed to snap shut. You are not catching it by surprise. You are walking directly into a prepared ambush. Temperature and the cycles of the tide further dictate the severity of these encounters. As cold-blooded invertebrates, crabs are slaves to the ambient temperature of their environment. In the heat of the afternoon, as the sun warms the shallow tide pools, their metabolic rate skyrockets. They become incredibly fast, highly reactive, and far more aggressive. Conversely, the stress of a low tide, which forces them to defend a rapidly shrinking puddle of oxygenated water, places them on a hair trigger. During these hot, shallow periods, which coincidentally is exactly when tourists and families are most likely to be walking the beaches, crabs are less likely to flee and infinitely more likely to stand their ground and fight. This behavioral intensity is also deeply tied to their social structure. Many crab species are highly territorial, engaging in constant, ritualized disputes and violent dominance displays with rival males. In these species, the males possess massively oversized claws that are strictly optimized for combat and force, rather than feeding. Grabbing one of these males, without understanding the profound difference in strength and temperament between sexes or species, dramatically escalates the risk. You're not just grabbing an animal. You're grabbing a gladiator that is biochemically and structurally primed for war. Yet, because these injuries do not involve venom, they are consistently downplayed. There is no dramatic bleeding, no systemic collapse, no rush into the hospital with a failing heart. There is only intense, localized pressure, a burst of pain, and a bruise. But the damage inflicted beneath the surface is often severe and long-lasting. When a heavy claw closes over the delicate joints of the fingers, it crushes the cartilage and deeply contuses the bone. The swelling that follows can severely limit movement in the hand for days or weeks. More insidious is the risk of infection. A crab's claw is a tool used to tear apart dead fish, crack open rotting shellfish, and sift through the detritus of the ocean floor. The serrated edges are caked in highly aggressive marine bacteria. When the claw breaks the skin, whether through a direct puncture or through the tearing action of a panicked victim pulling away, it drives those bacteria deep into the wound. The ocean is not sterile. Small cuts introduced by crab claws frequently become red, swollen, and fiercely infected, particularly in warm, tropical environments where bacterial loads are exceptionally high. What begins as a moment of surprise in a tide pool can easily evolve into a week-long battle with localized tissue infection requiring heavy antibiotics. This reality completely shatters the cultural framing of crabs as playthings or easy, casual food. In recreational crabbing and tide pooling, people scoop them up with bare hands, reach blindly into traps, or grab them from above, operating under the false assumption that they are in complete control. They assume that a crab cannot reach backward, or that its joints are limited in their range of motion. This is a painful misconception. Crabs possess highly articulated shoulders. They can rotate those massive claws incredibly far back over their own carapaces, reaching angles that constantly catch amateur handlers off guard. Even thick gloves offer limited protection against the sheer compressive force, especially if the claw manages to close directly over a knuckle or the bed of a fingernail. where the padding is compressed instantly and the force transfers straight to the bone. Children are uniquely, tragically vulnerable in these environments. Driven by an innate curiosity that completely overrides caution, they treat the tide pool as a playground. Their small, delicate hands fit perfectly into the dark crevices where the largest crabs retreat. A child reaching for a crab expects a toy. They do not expect the sudden, vice-like agony of a crushing injury. When that pain arrives, the child panics instantly. They scream. They yank their arm back wildly, and the crab locks down harder. The situation spirals into chaos, often resulting in severe lacerations of the child's fingers, and occasionally leading to secondary injuries when adults rush frantically over slippery, algae-covered rocks to intervene, falling and injuring themselves in the process. It is a chain reaction of harm, rooted entirely in a human misunderstanding of what a crab actually is. In professional fishing communities, this misunderstanding does not exist. Experience has bred a deep, practical respect for the animal's anatomy. Professionals use tongs. They use heavy calipers. If they must use their hands, they grip the crab firmly from the very back of the carapace, entirely out of the rotational reach of the claws. They do not treat the animal as a joke. They treat it as a hazard. Where this generational knowledge is respected, injuries are rare. Where it is ignored, replaced by the casual arrogance of a beachgoer wanting a photograph, the exact same painful lessons are taught over and over again. The crab is not a villain. It is not malicious, and it does not seek out human fingers to crush. It is simply an uncompromising entity. It is a biological machine designed to survive in a brutal, pounding environment where softness is a death sentence. Its claws exist to crush, to cut, and to hold, and they will execute that function with flawless, unthinking efficiency whenever the opportunity is presented. Underestimating a crab does not make it weaker. It simply places human flesh directly into the path of a system optimized for destruction. In the end, the crab teaches one of the simplest, yet most frequently ignored lessons of the coastal ecosystem. Danger does not scale with physical size, and it does not care about your perception of its appearance. Danger scales with mechanical function. A small animal, equipped with the right evolutionary tools, can inflict serious, lasting harm when those tools are disrespected. The tide pools may look like playgrounds, flooded with sunlight and gentle ripples, but they are ancient arenas. They are shaped by survival pressures far older than human curiosity. The crabs that patrol these margins enforce their boundaries without a shred of hesitation. For anyone reaching down into the shallow water with bare hands, the warning is not written in bright venomous colors or announced with a terrifying roar. It is written in the geometry of the shell and the silence of the waiting claw, because the crab does not bluff. And once that biological press closes, it almost never lets go. Watch the edge of the reef, where the vibrant coral drops off into the terrifying blue of the open ocean. This is a patrol route. The barracuda does not hide in crevices. It does not scuttle along the bottom. It holds its position in the middle of the water column, an absolute master of its domain. Its body is a torpedo of pure, rigid muscle, wrapped in scales so brilliantly silver they act as a living mirror, reflecting the surrounding water and making the fish almost invisible until it is right on top of you. Its jaw hangs slightly open, revealing rows of teeth that look like shattered glass. It moves with a slow, deliberate confidence, completely devoid of the frantic, nervous energy that consumes the smaller fish darting through the coral below. It is a predator built for explosive, straight-line violence. But the physical danger of the barracuda, its speed, its teeth, its predatory instinct, is an illusion. It is a distraction. The true horror of this animal has absolutely nothing to do with being bitten. The true horror begins when you pull out of the water, bring it to the kitchen, and put it on a plate. When you look at a freshly caught barracuda, every single human instinct tells you that it is a magnificent source of food. It looks incredibly healthy. The meat is firm, snow-white, and smells only of the clean, salty ocean. There is no rot. There is no discoloration. There is no foul odor to warn you away. It looks like exactly the kind of prize catch that anchors a feast, the kind of premium reef fish that tourists pay high prices for in seaside restaurants. This visual perfection is the setup for one of the most profound betrayals in the natural world, because locked deep inside the cellular structure of that flawless, mild-tasting fillet is an invisible, odorless, tasteless chemical payload that is about to systematically dismantle your nervous system from the inside out. This is saguaro poisoning. And what makes it uniquely terrifying is that it is not a contamination introduced by a dirty cutting board, poor refrigeration, or careless handling. It is a biological inevitability, a poison that began its journey years before the barracuda ever encountered a fisherman's hook. To understand how a perfectly healthy-looking fish becomes a neurotoxic weapon, you have to look past the barracuda and peer into the microscopic foundation of the reef itself. Saguaro does not begin with the fish. It begins with microscopic organisms called dinoflagellates. These invisible single-celled organisms attach themselves to the surface of marine algae, specifically the types of algae that colonize dead or broken coral. In a perfectly pristine, undisturbed coral reef, these dinoflagellates exist in relatively low numbers, but the ocean is rarely pristine anymore. When a reef is physically damaged by a massive hurricane, when it is bleached white by warming ocean temperatures, or when it is choked by agricultural runoff and pollution from the shoreline, the coral dies. And when coral dies, algae immediately moves in to cover the skeleton. This explosion of algal growth creates a massive, sprawling habitat for dinoflagellates to rapidly multiply. These microscopic organisms produce a highly complex chemical compound called ciguatoxin as a defensive mechanism. And here is where the slow, invisible chain reaction begins. Small, herbivorous reef fish swim along the damaged coral, grazing on the algae. As they eat the algae, they also consume the dinoflagellates and the ciguatoxin. The toxin does not kill these small fish. Their physiology can tolerate it in tiny doses. Instead, the toxin is absorbed and stored in their fat and muscle tissue. Then, slightly larger carnivorous fish eat the grazers. Because ciguatoxin is incredibly stable and fat-soluble, it doesn't break down during digestion. It transfers from the prey into the predator, pooling in higher concentrations. This process is called biomagnification. With every step up the food web, the toxin becomes denser, more concentrated, and more dangerous. Which brings us back to the barracuda. As an apex or near-apex predator, the barracuda is a highly opportunistic hunter. It sits at the very top of the local food chain, consuming thousands of smaller fish over its long lifespan. It is the ultimate accumulator. Every toxic meal its prey ever ate is deposited directly into the barracuda's flesh. The older and larger barracuda, the more chemical history it carries. The fish itself suffers absolutely no ill effects. Its sodium channels are slightly different than ours, making it immune to the poison. To the barracuda, it is just food. To a human, it is a loaded gun. When that large, impressive barracuda is hauled onto the deck of a boat and sold to a restaurant, the trap is fully set. In the kitchen, human ingenuity fails completely. We rely on cooking to save us from the dangers of a natural world. We believe that fire purifies. We believe that if we grill, fry, bake, or boil our food, we destroy the bacteria and neutralize the toxins. Ciguatoxin makes a mockery of human culinary techniques. The molecule is violently heat-stable. You can subject a fillet to roaring flames. You can deep fry it in boiling oil. You can bake it for hours, and the toxin will remain perfectly intact. Freezing it does nothing. Marinating it in high-acid citrus juices does nothing. The poison is fundamentally woven into the protein of the fish. The meal is served. The diner takes a bite. The fish tastes magnificent, mild, flaky, and delicate. The brain registers a satisfying, nourishing experience. The plates are cleared. The bill is paid. The diners go to sleep, completely unaware that a biological bomb has just detonated in their bloodstream. The onset of saguaro is cruel in its delay. It waits. It allows the victim to separate the cause from the effect. Hours, sometimes up to a full day later, the first symptoms strike. Usually, it begins in the gastrointestinal tract. Severe nausea, crippling abdominal cramps, vomiting, and diarrhea. In the early hours, the victim almost always misdiagnoses themselves. They assume it is just standard food poisoning, perhaps a bad clam or a dirty kitchen. They assume it will pass in a day or two. But ciguatoxin is not a digestive irritant. It is a highly specialized neurotoxin. And once it finishes passing to the stomach lining and enters the nervous system, the true nightmare begins. The toxin targets the voltage-gated sodium channels in the human nervous system. These are the microscopic doorways on the surface of your nerve cells that open and close to transmit electrical signals. Ciguatoxin forcibly binds to these doorways and props them wide open. It forces the nerves to fire continuously, chaotically, and without any external stimulation. The electrical wiring of the human body is essentially short-circuited. As the gastrointestinal distress fades, the neurological symptoms rise to take its place, and they're so bizarre, so fundamentally alien, that they induce a profound psychological terror. It usually begins with severe, vibrating numbness and tingling in the lips, tongue, and throat. This spreads rapidly to the hands and feet. The muscles become profoundly weak. Victims report a heavy, aching exhaustion in their joints that makes walking feel like wading through wet concrete. But the hallmark of ciguatera poisoning, the symptom that sets it apart from almost every other illness on Earth, is a terrifying phenomenon known as temperature reversal. Because the nerves responsible for perceiving temperature have been chemically hijacked, the brain's ability to interpret reality is completely scrambled. When the victim touches something cold, the corrupted nerves misfire and send a screaming signal of intense heat to the brain. A cold glass of water feels like it is boiling. Stepping onto a cool tile floor feels like walking on burning coals. Taking a cold shower feels like being doused in scalding acid. Conversely, warm objects feel like dry ice. The ambient air temperature becomes a source of agony. The very fabric of sensory reality is turned inside out. The victim's skin is perfectly fine. There are no burns. There is no frostbite. But the mind is trapped in a funhouse mirror pain, where every physical interaction with the world delivers the exact opposite sensation it is opposed to. This sensory inversion strips away the victim's trust in their own body. Eating becomes a terrifying ordeal, as cool foods burn the mouth and warm foods feel freezing. The simple act of washing hands becomes a psychological hurdle. And unlike a bacterial infection that can be cleared with a round of antibiotics, ciguatera has no cure. There is no antivenom. There is no pill that can pry the toxin out of the sodium channels once it is locked on. The medical field is largely reduced to offering supportive care, intravenous fluids for dehydration, and medications to slightly dull the nerve pain. The victim simply has to wait for their body to slowly, painstakingly regenerate the damaged nerve channels over time. That time is not measured in days. It is measured in weeks, months, and in severe cases, years. The persistence of ciguatera is what transforms it from a bad medical event into a chronic, life-altering condition. Long after the initial poisoning, when the victim believes they have finally recovered, the symptoms can violently return. The toxin is fat-soluble, meaning the body stores it deep within its lipid reserves. Any event that alters the body's metabolism can pull the poison back into the bloodstream, triggering a full-blown relapse. A rigorous workout at the gym can bring back the tingling and the burning. Consuming alcohol, eating nuts, or even eating completely safe, non-toxic seafood can cause a temperature reversal to flare up again. The victim is forced to navigate the world on a knife's edge, constantly terrified that a simple meal or a brisk run will throw them back into the neurological abyss. Their relationship with food, particularly with the ocean, is permanently fractured. The sea is no longer a source of bounty. It is a source of invisible, lurking trauma. From a broader, ecological perspective, the barracuda is completely innocent in this dynamic. It is not trying to poison humanity. It is merely a messenger, carrying a chemical warning from a dying reef to the dinner table. The prevalence of ciguatera is a direct reflection of the health of the coral ecosystem. In regions where the reef is thriving, where the water is clean and the coral is intact, the dinoflagellates are kept in check, and the fish are safe. But in regions where humans have dredged the coastlines, dumped agricultural waste into the sea, or allowed ocean temperatures to spike, the algae blooms, the dinoflagellates multiply, and the food web becomes toxic. The poison barracuda is the final, unavoidable consequence of environmental degradation. We break the reef produces a toxin, the fish absorb the toxin, and we eat the fish. It is a closed, perfect loop of biological retribution. This reality is deeply understood by indigenous coastal communities and generations of local fishermen. In areas prone to ciguatera, there is a profound, hard-won respect for mechanics of biomagnification. Locals will readily eat small, young barracuda, knowing they have not lived long enough to accumulate a dangerous dose. But if a massive, ancient 5-foot barracuda is hauled onto the dock, the locals will not touch it. They understand that a fish that large is a swimming chemical repository. They know that its size is a liability, not a luxury. But modern tourism and globalized seafood markets frequently ignore this generational wisdom, driven by the aesthetic appeal of massive catch, and the premium prices that tourists are willing to pay for a dramatic, center-of-the-plate spectacle. Restaurants will eagerly purchase the largest predators the ocean can provide. The tourist, sitting in a beautiful resort, assumes that a high price tag guarantees safety. They equate luxury with purity. The barracuda shatters that illusion. It proves that biology does not care about your wealth, your vacation, or the skill of the Michelin-starred chef in the kitchen. The danger of the barracuda is not the terrifying jaws that part the water. It is a silent, invisible accumulation of the ocean's damage, woven so perfectly into flesh that you cannot see it until it's far too late. It is a predator that strikes not from the shadows of the reef, but from the center of the dinner plate, hours after you have swallowed it. It leaves you alive, but trapped in a malfunctioning body, a living testament to the fact that when we degrade the foundation of the ocean, the top of the food chain becomes a weapon turned directly back on us. To understand the cuttlefish, you must first abandon the idea that an animal needs teeth, venom, or brute strength to be dangerous. Down in the shallow coastal waters, hovering just above the seagrass beds and the shifting sand flats, the cuttlefish drifts like a living hallucination. It does not swim so much as it manifests, its body rippling with waves of color and texture that seem to defy the physics of light. It occupies a liminal space in the ocean, not truly anchored at bottom like a crab, yet not endlessly cruising the open blue like a shark. It exists in the margins, suspended in the sunlit shallows where predators are abundant and the line between safety and consumption is razor thin. To the human eye, whether viewed through a diver's mask or hauled up dripping onto the deck of a boat, the cuttlefish appears utterly, enchantingly harmless. It has no armored shell. It boasts no massive, crushing claws. It does not carry the chemical doomsday payload of the pufferfish or the hidden, hypodermic agony of the stingray. It is soft, rounded, and its movements are so gentle they feel almost hypnotic. This perception of beauty and vulnerability is the ultimate trap. It is exactly what makes handling a cuttlefish so inherently hazardous. Because the cuttlefish's survival strategy is not built on confronting predators. It is built on seizing total control of the situation and actively generating absolute chaos the moment that control is threatened. The secret to this control lies buried deep inside the animal's mantle. Unlike its close relatives, the octopus and the squid, the cuttlefish possesses a highly specialized internal structure known as the cuttlebone. This is not a bone in a mammalian sense, but rigid, incredibly porous, chalky shell that the animal uses as a master buoyancy compensator. By actively pumping gas and liquid in and out of the microscopic chambers of this internal shell, the cuttlefish can achieve perfect, effortless neutral buoyancy. It can hover an inch above the seafloor, without moving a single muscle, suspended like a ghost. This perfect hovering is what brings it into direct conflict with human industry. Because it holds its position so quietly just above the substrate, it rests exactly in the path of bottom-trawling nets, crab traps, and fishing lines. It does not dart away when the heavy gear approaches. It simply tries to blend in, remaining completely unnoticed until it is violently scooped up, trapped in a tangled mass of nylon, and dragged from the calm, weightless ocean up into the harsh, gravity-heavy world of fishing boat. When a cuttlefish is dumped onto a deck, the illusion of the gentle, beautiful creature evaporates instantly. The human handler reaches down, expecting a passive, helpless lump of seafood. What they grab instead is an animal whose entire biology is wired to destabilize its attacker. The first weapon deployed is psychological, delivered through the most advanced skin in the animal kingdom. A cuttlefish is covered in millions of microscopic, pigment-filled sacs called chromatophores, layered over deeper reflective cells called iridophores and leucophores. In the water, these cells work in perfect harmony to mimic the exact texture and shadow of the surrounding reef. But on a boat, under the extreme life-or-death stress of capture, the cuttlefish abandons camouflage and switches to sensory overload. In a fraction of a second, The animal's skin violently flashes with high contrast, strobing patterns, stark, pulsating waves of black and white that roll across its body like static on a broken television. For a human handler reaching into a dark net, the sudden, erratic explosion of visual noise is incredibly jarring. It triggers a deep, hardwired startle reflex. The handler flinches. They hesitate, and in a slippery, confined environment, hesitation is a first step toward an accident. As the handler's hand finally makes contact, they encounter the second layer of defense. A cuttlefish is phenomenally, impossibly slippery. It possesses no scales to grip. Instead, its soft, heavily muscled mantle is coated in a thick, highly specialized layer of mucus. This slime is not an accident in biology. It is a friction-reducing armor designed specifically to allow the animal to slide seamlessly out of the jaws of a shark or the grasping tentacles of a larger predator. When a fisherman tries to grab a live cuttlefish with bare hands or even heavy rubber gloves, it feels like trying to hold on to a pressurized water balloon coated in heavy grease. As the human fingers squeeze, try to establish a firm grip, the cuttlefish utilizes its lack of a rigid skeleton to compress its internal organs, flattening its body and actively slipping through the gaps in the handler's fingers. And right at the exact moment the human grip falters, the cuttlefish fires its primary engine. Beneath its head, the cuttlefish possesses a highly muscular siphon. It draws water deep into its mantle cavity, sealing the edges tight, and then violently contracts its muscles, expelling the water through the siphon in a high-pressure jet. While a cuttlefish cannot sustain high-speed swimming over long distances, its short-range, explosive acceleration is staggering. With a sudden, powerful thrust, the slippery animal launches itself completely out of the handler's grasp. It does not jump, it rockets. A 5-pound block of solid, with muscle ricocheting across the deck of a boat. This is where the physical danger to the human peaks. The danger does not come from the cuttlefish attacking the human. The danger comes from a human reacting to the cuttlefish. Imagine the environment: a commercial fishing deck or a small skiff. The surface is already slick with seawater, fish slime, and algae. The boat is pitching and rolling with the ocean swell. The space is cramped, filled with sharp hooks, heavy lead weights, exposed winch gears, and open coolers. When the cuttlefish suddenly blasts out of the handler's hands, human reflex takes over. The handler violently lunges to catch the escaping catch. They twist their torso. They throw their weight forward on a wet, unstable surface. Feet slide, ankles roll, knees slam into metal bulkheads. In the desperate, flailing attempt to recapture an animal that has essentially turned itself into a kinetic projectile, fishermen fall. They drop razor-sharp fillet knives, which clatter dangerously around their boots. They trip over coiled ropes, risking severe entanglement. The cuttlefish causes blunt force trauma, lacerations, and musculoskeletal injuries without ever laying a single aggressive tentacle on the person it is defending itself against. And if the physical escape is not enough, the cuttlefish deploys its ultimate mechanism of disorder, the ink. When a cuttlefish feels its escape is blocked, it ruptures an internal sac, venting a dense, viscous cloud of sepia directly through its siphon. Underwater, this ink performs a dual role. It creates a massive, opaque smoke screen that blinds a predator, and it coagulates into distinct, physical shapes called pseudomorphs, dummy targets that look and feel exactly like the cuttlefish, designed to trick a predator into biting a mouthful of nothing while the real animal jets away in a different direction. But when that ink is fired in the air on the deck of a boat, the effect is catastrophic. The ink splatters across the deck, coating everything it touches. It hits the handler's face, their safety glasses, their gloves. It is an incredibly dark, oily, and highly persistent fluid. Suddenly, the already treacherous footing of the boat deck is painted with a slick, friction-destroying lubricant. A fisherman taking a step backward to avoid the sudden blast of ink finds their boot completely lacking traction. They go down hard. Furthermore, this ink is not just colored water. It is a biologically active, chemically complex defense mechanism. It contains high concentrations of tyrosinase and other compounds designed to overwhelm the chemical receptors of marine predators. If this ink gets into a human eye, a very common occurrence when an animal jets violently from waist height, it burns. It acts as an aggressive irritant, causing the eye to water profusely, forcing the handler to drop whatever they are holding and rub their face, rendering them temporarily blind in an environment where vision is absolutely critical to survival. If the cuttlefish is dumped into a holding tank or a sorting bucket with other live catch, it will instantly ink the water, turning the entire container pitch black. This seemingly minor inconvenience becomes a serious hazard when handlers are forced to blindly reach their hands into opaque, black water that might also contain the crushing claws of crabs, the venomous spines of hidden lionfish, or the razor-sharp gill plates of thrashing snapper. The cuttlefish's defense mechanisms essentially blindfold the humans working around it, massively compounding the risk of every other animal on the deck. The unpredictability of this animal is deeply tied to its highly advanced sensory perception and its surprisingly complex intelligence. As ectothermic creatures, their metabolism is entirely dictated by the temperature of the water. In the early morning, when the coastal waters are cool, a cuttlefish hauled aboard might appear sluggish, pliable, and entirely defeated. A handler might comfortably toss aside, assuming it poses no challenge. But as the sun rises and the shallow waters warm, their internal engines rev up. A cuttlefish caught in the afternoon is a completely different animal, hyperreactive, lightning fast, and deeply uncooperative. You cannot standardize your approach to a cuttlefish because the animal itself is constantly shifting its baseline based on the ambient environment. More importantly, a cuttlefish sees the world in a way that is fundamentally alien to human biology. Their massive W-shaped pupils do not process color the way we do, but they are incredibly sensitive to polarized light and microscopic shifts in contrast. This means that a human moving across a boat deck, casting a shadow, or wearing sunglasses that reflect light appears as a massive high-contrast, terrifying threat to the cuttlefish. You might think you are moving slowly and calmly, but to the cuttlefish's hyper-advanced visual cortex, you are screaming an aggressive signal. This sensory mismatch explains why cuttlefish seem to explode into action out of absolutely nowhere. They are reacting to visual triggers that we cannot even perceive. And because they possess a decentralized nervous system, much like the octopus, their reaction time is staggering. They do not have to think about jetting away. The visual stimulus bypasses complex processing and triggers an immediate, reflexive muscular explosion. Even in the kitchen, the danger persists. The nervous system of a cephalopod is incredibly robust, and the muscles do not simply shut down the moment the animal is considered dead. A chef tasked with cleaning a freshly caught cuttlefish faces a slippery, unyielding puzzle. A dull knife will not pierce the rubbery mantle, requiring the chef to apply significant downward pressure. If the mucus-coated body slips just a fraction of an inch under that pressure, the knife shears off course, often straight into the hand holding the animal. If the ink sac is accidentally nicked during the cleaning process, it can burst, instantly covering the cutting board, the knife handle, and the chef's hands in a slippery black slick, guaranteeing that the next cut will be incredibly dangerous. The cuttlefish completely rewrites the rules of engagement. We are conditioned to fear the animals that want to bite us, sting us, or crush us. We respect the shark because of its teeth. We respect the stingray because of its barb. But the cuttlefish demands respect through its absolute mastery of evasion and environmental disruption. Its dirty tricks are not malicious. It does not want to hurt the fishermen. It simply refuses to be controlled. The ink, the slipperiness, the strobing colors, and the jet propulsion are elegant, perfectly refined solutions to the problem of surviving in an ocean that constantly wants to eat it. When those elegant solutions are unleashed in the cramped, dangerous, gravity-bound world of human industry, they turn the environment itself into a weapon. In the broader narrative of the ocean, the cuttlefish serves as a brilliant, messy reminder that lethality is not the only measure of danger. Sometimes, the most hazardous thing you can encounter is an animal that completely shatters your illusion of control. It exposes human clumsiness. It turns our reflexes against us. It makes us slip, stumble, and fall over our own feet. The cuttlefish proves that you do not need a fight to win. You only need to cause enough confusion, create enough disorder, and leave the deck so thoroughly coated in slick black chaos that by the time the humans finally regain their footing, you have already slipped quietly back into the sea. If you look into the darkest, most cavernous architecture of the coral reef, The deep overhangs, the sunken caves, the structural foundations where shadows gather and the ocean current slows to crawl, you will find the undisputed monarch of the benthic world. The grouper does not patrol the open water. It does not dart or chase. It holds court. Its body is an absolute monument to brute force and stability. Built more like an armored vault than a streamlined fish, it moves with deliberate, heavy economy, refusing to waste a single ounce of energy on unnecessary motion. Its massive, oversized eyes track the surrounding water with a calm, ancient authority. Its cavernous jaw opens just a fraction to ventilate its gills, hinting at a terrifying capacity for destruction. When you encounter a massive grouper underwater, you're not just looking at a fish. You're looking at gravity-made flesh. To the human eye, both above and below the surface, this imposing physical presence translates instantly into one specific concept: value. In the global seafood market, in the bustling fish auctions, and in the neon-lit tanks of high-end luxury restaurants, the grouper is the ultimate prize. Size suggests quality. Bulk suggests abundance. Age implies a premium texture and flavor. It looks like the quintessential dinner fish, the kind of centerpiece meal ordered to seal business deals, celebrate anniversaries, and signal prosperity. A massive 100-pound grouper displayed on a bed of crushed ice is a spectacle. It commands a breathtaking price tag, purchased under the deeply flawed human assumption that the most expensive, most impressive thing on the menu must inherently be the best. What the price tag does not tell you, and what the pristine, snowy white fillets will never reveal, is that buying the biggest, oldest grouper on the market is one of the most dangerous games of biological roulette a human being can play. The grouper is a masterclass in deception, not because it hides its teeth, but because its flesh is a perfect, invisible spawn for an ecological nightmare. Just like the barracuda, the grouper is a primary carrier of saguaro poisoning. But the specific biology, hunting strategy, and lifespan of the grouper elevate this chemical risk to an entirely different magnitude. Saguaro begins invisibly, at the very bottom of the food chain, with microscopic, toxin-producing dinoflagellates that cling to the algae covering damaged coral reefs. Small, grazing fish eat the algae, absorbing the ciguatoxin into their tissues. Slightly larger predators eat the grazers, and at the very top of this pyramid sits the grouper. But a grouper is fundamentally different from a pelagic hunter that roams across entire ocean basins. Groupers are fiercely territorial and highly site-attached. Once a grouper finds a favorable cave or ledge, it may stay within that exact same tiny radius of the reef for years, sometimes for its entire life. It does not migrate. It does not dilute its diet by traveling. Furthermore, the hunting strategy of the grouper is based entirely on the ambush. It waits in the shadows until a smaller fish, a crustacean, or an octopus wanders just a fraction of an inch too close. Then, with a speed that defies its massive bulk, the grouper opens its cavernous mouth and violently flares its gills. This creates a massive, instantaneous vacuum. The prey is not bitten. It is literally inhaled, sucked into the crushing grip of the grouper's pharyngeal teeth faster than the human eye can process. This unmatched efficiency means the grouper consumes a massive cross-section of the local reef population. And because it stays in one place, it eats from the exact same chemical buffet, day after day, year after year, decade after decade. Groupers are incredibly long-lived animals. A truly massive specimen, the exact kind prized by luxury seafood markets, could easily be 30 or 40 years old for 3 or 4 decades. That animal has been accumulating every microdose of ciguatoxin present in its territory. The toxin is fat-soluble and highly stable. It does not pass through the grouper. It locks into its tissues. Through the relentless math of biomagnification, the older and larger the grouper gets, the more neurologically devastating its flesh becomes. The grouper itself is completely immune. It suffers no illness, no neurological breakdown. It simply becomes a living, swimming chemical ledger of the reef's entire toxic history. When a tourist points to the largest fish in the restaurant tank, they believe they are ordering the pinnacle of luxury. In biological reality, they are ordering a 30-year backlog of concentrated neurotoxin. The betrayal of the meal is absolute. The fish arrives at the table perfectly prepared. The meat of a large grouper is legendary for its firm, sweet, large flake texture. Cooking it no matter the method, does absolutely nothing to neutralize ciguatoxin. The poison laughs at boiling water. It easily survives the searing heat of a grill. Freezing the fish for months only preserves the poison in perfect stasis. Because the toxin has no odor, no color, and no flavor, the diner enjoys every single bite. They pay a massive bill, completely satisfied, operating under the deeply ingrained psychological safety net that an expensive, professionally cooked meal in a high-end establishment cannot possibly hurt them. The collapse of that illusion usually begins in the middle of the night. The onset of siguata from a massive grouper is often catastrophic. It starts with a visceral, violent rejection of the gastrointestinal system, intense nausea, crippling abdominal pain, and relentless sickness. But this is merely the preamble. As the ciguatoxin floods the bloodstream and crosses into the nervous system, it begins its true work, locking open the voltage-gated sodium channels of the nerve cells, forcing the entire electrical grid of the human body to misfire simultaneously. The victim begins to experience profound, terrifying numbness spreading across their face, lips, and tongue, soon radiating down into their hands and feet. This is followed by a crushing, leaden weakness in the skeletal muscles. Walking to the bathroom becomes an exhausting, Herculean effort, and then the ultimate horror of the toxin fully engages. The total inversion of sensory reality. The brain loses its ability to accurately interpret temperature. A victim stepping onto a cold bathroom floor will scream in agony, feeling as though they had just stepped onto a red-hot iron skillet. Splashing cool water on their face feels like being attacked with acid. Reaching for a warm blanket induces violent, freezing shivers. The nervous system is completely stripped of its reliability, turning the most basic, comforting interactions with the physical world into a gauntlet of pain. For the diner who paid hundreds of dollars for a premium culinary experience, the psychological toll is devastating. They are trapped inside a body that is transmitting pure chaos. And because there is no known antidote, no pharmaceutical reset button to flush the toxin from the locked nerve channels, they are forced to simply endure. The medical establishment can offer 4 fluids and basic pain management, but the only true cure is time. And siguata poisoning from a large, heavily loaded apex predator, like a massive grouper, does not resolve in days. The agonizing temperature reversals, the muscle weakness, and the nerve pain can persist for months. In some cases, victims suffer agonizing relapses years later, triggered by something as simple as drinking a beer, eating a piece of chicken, or pushing themselves too hard in a workout, which pulls the dormant toxin back out of their fat stores and into their bloodstream. The contrast between the local wisdom of coastal communities and the hubris of the global luxury market is striking. In regions where fishermen have lived alongside the reef for generations, the rules are deeply understood without the need for microscopes or toxicology reports. Locals will happily catch and consume a small, young grouper, knowing its chemical history is short. But if they pull up a massive, ancient behemoth, they will cut the line or throw it back. They know that size is a liability. They know that the biggest prize carries the heaviest curse. But the international market does not care about local wisdom. The market cares about spectacle. Restaurants and distributors demand the giants because tourists and wealthy diners demand the giants. This relentless economic pressure drives a wedge between biological reality and human consumption, turning a profound ecological warning sign into a status symbol. This insatiable demand for the largest groupers triggers a secondary, entirely distinct tragedy: the collapse of the reef itself. Groupers are central regulators of the marine ecosystem. By ambushing mid-sized fish, they prevent any one species from overpopulating and throwing the fragile coral environment out of balance. When humans systematically hunt down and remove the largest, most successful groupers to feed the luxury seafood market, they are removing the reef's most vital architects. Without the apex predator, the populations of smaller, algae-grazing fish can fluctuate wildly. The delicate balance shifts. If the reef is already stressed by warming waters or pollution, the algae grows out of control. And as the algae spreads, the microscopic dinoflagellates that produce ciguatoxin multiply by the billions. By paying top dollar to eat the massive grouper, humans actively accelerate the exact environmental degradation that creates the poison in the first place. It is a perfect, vicious cycle of ecological irony. We remove the immune system of the reef to decorate our dinner plates, and in return, the reef poisons us. The grouper itself remains entirely indifferent to this narrative. It is not a malicious creature. It is simply a master of its environment, shaped by millions of years to grow large, stay perfectly still, and consume whatever crosses its path. It is a biological vault, keeping a perfect, silent record of everything that happens in the shadows of the coral. When a human decides to break open that vault and consume its contents, they are not just eating fish. They are eating the cumulative history of the reef's invisible chemistry. They are swallowing decades of accumulated toxins, packaged perfectly inside a snowy white, expensive fillet. The story of the grouper is the story of human arrogance colliding with natural consequence. It is a hard, uncompromising proof that nature does not negotiate with our economics, our culinary traditions, or our desire for luxury. In the ocean, the biggest, most impressive prize is rarely a reward. It is almost always a trap. And for those who insist on chasing the spectacle of the giant dinner fish, the grouper delivers a slow, agonizing reminder that some things belong to the deep, and taking them costs far more than the price on the menu. Down on the continental shelves, where the light struggles to penetrate and the seafloor dissolves into rolling plains of mud and silt, the concept of a predator takes on a completely different shape. In this muted, monochromatic world, speed is a waste of precious energy. Here, the most successful hunters do not chase. They disappear. If you were to stare directly at a monkfish resting on the bottom of the ocean, your brain would likely refuse to register it as a living organism. It does not possess the sleek, silver torpedo shape of a tuna, nor the terrifying, muscular grace of a shark. It looks entirely like a mistake. It is a broad, flattened mass of flesh that mimics the sediment with terrifying accuracy. Its skin is a mottled, warty tapestry of mud browns and dull greens, its edges fringed with fleshy flaps that blur the outline of its body, melting it seamlessly into surrounding debris. To a passing fish or a human observer, it looks like a discarded piece of rot, a heavy stone, or something that died a very long time ago. This absolute commitment to looking like a piece of the inanimate seafloor is the foundation of the monkfish's existence. It is the ultimate ambush predator, a creature that has traded every ounce of agility for the ability to become a biological trap. The anatomy of this animal is wildly disproportionate. It is almost entirely composed of a massive, flattened head and a cavernous mouth, trailing a tapering, muscular tail. That mouth is so wide, so impossibly large, that it seems to violate the physical boundaries of the fish's own body. And lining those massive jaws are rows of needle-sharp teeth that curve aggressively inward, pointing directly down toward the throat. These teeth are not meant for slicing or chewing. They are structural bars on a one-way cage. The monkfish does not prowl. It flattens itself against the mud and deploys a single deceptive tool, a modified dorsal spine located just above its mouth. This spine acts as a built-in fishing rod, tipped with a small, fleshy lure that wiggles invitingly in the current. And then the fish waits. It can wait for an eternity, completely motionless, breathing so shallowly that it doesn't disturb a single grain of sand. When a curious fish or crustacean drifts close to investigate the dancing lure, the monkfish does not lunge. It simply opens its cavernous jaw. The sheer speed and volume of this expansion create a massive, instantaneous vacuum in the water. The prey is not bitten. It is violently inhaled. The surrounding water, the sediment, and the victim are sucked into the black void of the mouth in a fraction of a second. The jaw slams shut. The inward curving teeth lock into place. The trap door is closed, and the monkfish goes back to being a lump of dead mud. It is a flawless system for the cold, dark bottom of the sea. But when this master of deception is dragged up from the depths and dropped onto the deck of a commercial fishing trawler, its survival strategy creates one of the most unpredictable and dangerous psychological traps a human can encounter. When a massive trawl net is hauled aboard, spilling thousands of pounds of thrashing, suffocating sea life onto the wet, pitching deck, the environment is pure chaos. Fish are flipping wildly, crabs are snapping, and fishermen are working with frantic speed to sort the catch, clear the gear, and reset the nets. In the middle of this frenzied, high-energy environment lies the monkfish, and it is doing exactly what evolution taught it to do. It is doing absolutely nothing. When hauled into the open air, the monkfish looks profoundly, unequivocally dead. Its flattened body is entirely limp. Its massive, dull eyes stare blankly at the sky. It does not thrash against the deck. It does not gasp dramatically. It does not flare its fins in a defensive posture. It presents itself as an inert, heavy lump of gelatinous flesh. This is a deception that catches even the most seasoned, callous fishermen completely off guard. Human beings are hardwired to associate movement with threat. A thrashing shark demands respect. A snapping moray eel demands distance. But a limp, motionless, ugly fish lying in a pile of kelp triggers a fatal sense of complacency. The human brain immediately categorizes the monkfish as a passive object. As the crew rushes to untangle the nets, hands reach down. They move quickly, blindly grabbing at the mesh, pulling fish aside, repositioning gear. A fisherman's hand moves into the zone directly in front of the monkfish's mouth. The monkfish may be pinned beneath 100 pounds of other fish. Its body might be awkwardly compressed by the heavy nylon mesh of the net, but its jaw mechanics are independent, completely unimpaired in waiting. It does not need to be swimming to strike. It does not need to be fully alert in a way we understand. It only requires proximity. Without a single twitch of warning, the massive jaw fires. The trap door slams shut on fingers, hands, heavy rubber gloves, or whatever tool happens to be in the way. The sheer crushing force of the bite is startling. But the true nightmare of a monkfish bite is the architecture of the teeth. Because the teeth curve sharply backward, they act exactly like fishhooks or barbed wire. When the jaw clamps down on a human hand, the immediate, overwhelming instinct of the fisherman is to violently yank their arm back. This is the worst possible thing you can do. The harder you pull, the deeper the inward-facing teeth dig into the flesh. Pulling away does not free you. It turns a crushing injury into a severe, tearing laceration. You are fighting against a mechanism designed specifically to ensure that once something enters the mouth, it can never, ever slip backward. The fish's powerful jaw muscles lock into a reflexive, unyielding grip. It does not let go. In many cases, the monkfish will begin a slow, powerful twisting motion, using its body weight to leverage the bite, further grinding the teeth against bone and tendon. The environment on the boat amplifies this danger exponentially. A fishing deck is slick with blood, water, and fish slime. It is rolling violently on the ocean swell. When a fisherman is suddenly, unexpectedly bitten by a dead fish, the shock triggers a full-body flinch. They stumble backward, desperately trying to shake the heavy animal off their hand. On an unstable deck, the sudden loss of balance is catastrophic. Men fall backward into heavy winches. They slip under the massive, swinging iron doors of the trawl gear. They drop razor-sharp fillet knives. The bite itself is agonizing, but the cascading chaos it creates on a working vessel can easily lead to broken bones, concussions, or a man going overboard. In the freezing environments where many monkfish are caught, the danger is compounded by the cold. A fisherman's hands are often numb from hours of pulling icy nets. The thick, rubber-coated gloves they wear provide a false sense of security, dulling their tactile feedback. When the monkfish clamps down, the numbness delays the brain perception of the pain. For a few critical seconds, the fisherman might not even realize they have been bitten. By the time the pain pushes through the cold, the teeth are already buried deep into the tissue, and the trap is fully secured. But the physical damage of the bite is only the first phase of consequence. The secondary threat lies in the invisible ecosystem that lives inside the fish's mouth. The monkfish is a benthic creature. It spends its entire life face down in the mud, breathing in sediment, eating bottom-dwelling scavengers, and accumulating a massive, highly aggressive microbial community inside its oral cavity. The teeth are coated in marine bacteria specialized in breaking down dead tissue in low-oxygen environments. When those teeth puncture a human hand, they do not just tear the skin. They act as dirty hypodermic needles, driving this aggressive bacteria deep into the crushed, traumatized muscle tissue. Because the bite involves severe crushing pressure, the blood vessels around the wound are often damaged, reducing circulation to the area. This creates a perfect, oxygen-deprived pocket for the marine bacteria to fester. If the wound is not immediately, thoroughly cleaned, a near impossibility on the deck of a commercial trawler in the middle of shift, The infection rate is extraordinarily high. What starts as a surprising, painful bite quickly swells into a severe, throbbing infection. Fingers turn black and blue. The tissue around the puncture marks becomes necrotic. A moment of complacency on the deck can easily result in weeks of heavy antibiotics, deep tissue scarring, and the permanent loss of mobility in the hand. The monkfish does not bite out of malice. It does not harbor hatred for the fisherman pulling the net. It is simply executing a biological program written millions of years ago in the silent, dark mud of the ocean floor. It is a creature that has mastered the art doing nothing until the exact moment doing something is absolutely fatal. When we interact with a monkfish, we are forced to confront a deeply ingrained, entirely flawed human assumption: the belief that death or the appearance of death equates to safety. We look at a limp, ugly mass of fish, stripped of its ocean, lie in a pile of netting, and we assume it is no longer a participant in the world. We assume the threat has been neutralized by the air and the lights of the boat. The monkfish punishes this assumption with ruthless efficiency. It proves that the most dangerous weapon an animal can wield is not speed, and it is not venom. The most dangerous weapon is our own lowered guard. To handle a monkfish safely requires overriding your own eyes. Experienced crews do not look at the limp body. They do not trust the dull, staring eyes. They secure the head immediately. They treat every single monkfish hauled onto the deck as a live, primed explosive, regardless of how dead it appears to be. They keep their hands completely clear of the jawline, using heavy hooks and tools to maneuver the fish, respecting the hidden geometry of the trap. The monkfish stands as a grim, uncompromising reminder of the ocean's true nature. It teaches us that danger does not always arrive with a thrashing tail or a terrifying silhouette. Sometimes, danger is perfectly content to lay still in the mud or on the wet deck of a boat, looking exactly like a piece of harmless debris. It is the monster you thought was dead, and it only needs you to believe the illusion for 1 second before the jaws snap shut. The shoreline is the great deceiver. When you stand at the edge of the ocean, where the waves finally break and roll themselves thin across the sand, the water feels entirely inviting. It is warm, sun-drenched, and shallow. The gradient of the beach is gentle. People wade out waist-deep, chatting, relaxed, completely abandoning the vigilance they might hold if they were swimming over a deep, dark reef drop-off. The shallows feel like a swimming pool with a sandy bottom. They feel like an extension of the beach, a human space. But the sandy bottom is not a human space. It is a highly specialized, fiercely contested biological zone. And buried just a few millimeters beneath the soft, rippling sand, perfectly camouflaged and entirely invisible to the waders above, is a creature that proves just how dangerous an assumption of safety can be. The stingray is a masterpiece of cryptic evolution. It is an animal that has taken the basic blueprint of a shark, flattened it like a pancake, and adapted it for absolute mastery of the ocean floor. Its entire existence is built around remaining unseen. When a stingray settles onto a sand flat or a shallow seagrass bed, it does not just sit on the bottom. It integrates itself into it. By rhythmically undulating the massive, fleshy margins of its pectoral fins, the ray creates a localized downward current, actively excavating the sand beneath it. It sinks into the depression, and the displaced sand settles back down over its back in a fine, obscuring dusting. Within seconds, the animal vanishes. Its edges are erased. Its coloration naturally mimics the exact mottled hues of the surrounding sediment. The only indications that a living creature is buried are two small, unblinking eyes scanning upward and the rhythmic, pulsing opening and closing of its spiracles, specialized breathing vents located on the top of its head that draw in clean water, bypassing the sand-choked gills underneath. In this buried state, the stingray is not hunting humans. It is resting, conserving energy, or waiting for the sun to drop, so it can begin hunting small crabs, worms, and mollusks hidden in the mud. It is deeply peaceful, relying on its invisibility to hide from the massive hammerhead sharks and other predators that patrol the coastline. But this flawless invisibility is the exact mechanism that puts it on a catastrophic collision course with human beings. We enter the water relying almost entirely on our vision to keep us safe. But staring down to the surface of the ocean is incredibly difficult. Wind ripples the water, creating a distorted, moving lens. The sun creates a blinding, impenetrable glare. And in the surf zone, the churning water kicks up suspended sand, turning the shallows murky. We cannot see the bottom, so we blindly step when a human foot comes crashing down to the water column and lands squarely on the center of the buried stingray's disc. The illusion of the peaceful shallows is shattered in a fraction of a second. To the stingray, the sudden, crushing weight is not a clumsy tourist. It is the jaws of an apex predator. It is a life-or-death crisis. The ray cannot swim away because it is pinned. It cannot bite because its mouth is located entirely underneath its body, pressed into the sand. It has only one option for survival, and it is an option it deploys with blind, reflexive, explosive violence. The stingray's weapon is not its tail. The tail itself is just a muscular whip. The true weapon is located about a third of the way down the tail's length. It is a rigid, heavily calcified spine, commonly called a barb. But calling it a barb feels like a tragic understatement when you examine its architecture. It is a biological dagger. The spine is constructed from vasodentin, a material similar to the enamel of human teeth, making it incredibly hard and capable of piercing dense bone. It is flattened, tapering to a razor-sharp point, and running along both lateral edges of this dagger are rows of vicious, backward-facing serrations. When the ray's body is stepped on, its powerful core muscles contract, whipping the long tail violently upward and forward over its own back, striking exactly where the crushing pressure is coming from. The speed of this strike is blinding. It is a pure, unthinking reflex. The rigid spine is driven with immense kinetic force straight into the human ankle, the calf, or the foot. It punches effortlessly through neoprene wetsuits, through rubber diving booties, and deep into the flesh. But the puncture itself is only the first phase of the trauma. Because the stingray's entire goal is to free itself and escape, the moment the strike lands, the animal instantly thrashes and pulls away. This is where the nightmarish design of the serrated edges comes into play. The spine is designed to go in smoothly, but it is explicitly engineered to cause catastrophic resistance on the way out. As the ray pulls its tail back, those backward-facing teeth catch on the human muscle, the tendons, and the skin. They tear, they shred, they pull the tissue outward, transforming what would have been a clean puncture wound into a severe, ragged, deeply traumatized laceration. In the violence of this struggle, the spine frequently snaps off entirely, remaining hopelessly embedded deep inside the victim's leg, locked into the tissue by its own serrations. And yet, the mechanical destruction of the strike is still only half of the weapon. The other half is chemical. Covering the spine is a thin, delicate sheath of integumentary tissue that houses a dense concentration of venom-producing cells. When the spine is driven into a victim, this sheath is violently ruptured and peeled back, dumping a highly potent protein-based venom directly into the deepest, most freshly traumatized parts of the wound. The pain that follows is not a gradual building sensation. It is immediate, absolute, and overwhelming. Victims routinely describe it as the most excruciating agony they have ever experienced, surpassing broken bones, kidney stones, and severe burns. The venom is a complex cocktail of enzymes designed to cause intense, localized cellular death and massive, uncontrolled inflammation. It feels as though a glowing hot coal has been embedded inside the muscle, and someone is actively turning the dial up. The pain radiates outward from the wound, traveling up the leg, causing the entire limb to throb with a deep, sickening intensity. Within minutes, the tissue around the laceration begins to swell massively, turning a sickly, mottled cyanotic color as blood flow is compromised and the venom begins breaking down the cells. The sheer, overwhelming magnitude of the pain triggers a systemic physiological panic. Victims standing in waist-deep water frequently collapse. They experience severe muscle cramps, hyperventilation, and cold sweats. Blood pressure can drop dangerously low as the body goes into shock, not necessarily from lethality of the venom, which is rarely fatal to humans unless it strikes a vital organ, but from the brain's complete inability to process the sheer volume of pain signals flooding the nervous system. If the victim manages to drag themselves out of the water, the medical nightmare on the sand begins. The instinct of those trying to help is almost always wrong. They see a bleeding, ragged wound, and if the spine is still embedded, they attempt to pull it out. Pulling a stingray barb out of the leg on a beach is a disastrous mistake. without surgical tools to widen the wound track. Pulling the serrated dagger backward simply causes the teeth to dig deeper, severing blood vessels and nerves that may have been spared in the initial strike. The barb must be left in place until a medical professional can safely remove it, often requiring an incision to release the grip of the serrations. The only effective, immediate first aid for a stingray envenomation is to submerge the limb in scalding hot water. Just like the venom of the lionfish and the stonefish, stingray venom is composed of heat-label proteins. Submerging the wound in water that is incredibly hot, just shy of causing thermal burns, begins to denature the venom, breaking down its molecular structure and slowly, painfully dialing back the agony. It is a desperate measure, holding a screaming, bleeding limb in a bucket of scalding water on a beach, but it is the only way to neutralize the chemical fire. But surviving the immediate strike and neutralizing the venom does not mean the ordeal is over. The ocean has one final, lingering consequence waiting in the wound. The stingray lives its life pressed into the sand, the mud, and the silt. Its barb is coated in a dense, highly aggressive biofilm of marine bacteria. When the spine tears into the human body, it injects these microbes deep into the crushed, necrotic tissue caused by the venom. The venom has already killed the surrounding cells, creating an oxygen-depleted dead zone perfectly suited for bacteria to thrive. Without aggressive, immediate medical intervention, deep wound irrigation, and powerful antibiotics, a stingray wound will almost certainly become violently infected. The bacteria present in warm coastal waters, particularly the Vibrio species, are incredibly fast-acting and tissue-destructive. A wound that is simply bandaged and ignored can rapidly evolve into severe cellulitis, deep tissue necrosis, and in extreme cases gangrene, threatening the entire limb. The recovery from a severe stingray strike can take months of wound care, physical therapy, and surgical debridement. This danger is not limited to tourists walking on the beach. In the commercial fishing industry, the stingray represents a frequent, chaotic hazard on the deck of a boat. When a trawl net or a seine is hauled aboard, it is often choked with hundreds of pounds of bycatch. Among the thrashing fish, the stingrays are pulled from the bottom, but on the hard, wet deck of a boat, the ray's behavior changes. It is no longer pinned underfoot in the sand. It is exposed, suffocating, and terrified. A stingray on a deck will violently flap its massive pectoral fins, launching its body into the air and indiscriminately whipping its tail in every direction. The tail becomes a blur of motion, a heavy, muscular pendulum swinging a serrated dagger through the air. Fishermen working in cramped quarters, trying to clear the nets, are forced to dodge these blind, high-speed strikes. A strike on a boat deck often hits higher on the body, the thigh, the groin, the abdomen, or the arm. And because the fisherman is usually wearing heavy oilskin gear, the serrated barb can catch the heavy fabric, driving the venom-soaked spine deep into the muscle and locking the heavy, thrashing animal directly to the fisherman's body. The chaos that follows, trying to secure a violently flapping 100-pound animal while it is actively barbed into a crew member's leg, is the stuff of maritime nightmares. And yet, despite the horrific mechanical trauma, the agonizing venom, and the risk of massive infection, the stingray is an animal of profound innocence. It does not lie in wait to ambush human beings. It does not guard territory with aggressive malice. It is a creature of absolute defense. Every single injury inflicted by a stingray on a wader is the result of a human being inadvertently crushing the animal's spine. The stingray is simply executing a hardwired reflex to save its own life. The tragedy of these encounters is rooted entirely in a failure of human awareness. We walk into the ocean as if we are walking across a paved parking lot. We stride confidently, lifting our feet and bringing them down heavily, entirely blind to the complex biological minefield hidden just millimeters beneath the sand. The prevention of this agonizing trauma is incredibly, almost frustratingly simple. It requires no armor, no special equipment, and no advanced training. It only requires a fundamental shift in how we move through a wild environment. It is called a stingray shuffle. Instead of lifting your feet and stepping down, you simply slide your feet forward, dragging them through the sand without lifting them off the bottom. By shuffling, you push the sand forward. You create a continuous, low-level vibration that alerts the buried ray to your approach. And more importantly, If your foot does make contact with a hidden ray, you bump into the side of its disc rather than pinning it to floor with your body weight. Given the chance, given the slightest warning, the stingray will choose flight over fight every single time. It will burst out of sand, a beautiful, ghostly shadow, and glide silently away into the deeper water, leaving you completely unharmed. The stingray represents a critical, unforgiving lesson about the boundary between the human world and the wild ocean. The shallows are not a swimming pool. The sand is not empty. When we cross the surf line, we are entering a wilderness that operates on ancient, unyielding rules. The stingray does not ask for your respect. It simply demands your awareness. And for those who refuse to shuffle, for those who blindly step where they cannot see, the ocean's retaliation is swift, mechanical, and excruciatingly clear. The danger does not come from a monster in the deep. It comes from the quiet, hidden margins, waiting just beneath the surface, armed with serrated dagger, waiting for a single heavy footstep. Far below the surface, where the light surrenders to a heavy, crushing darkness, the ocean floor is a landscape defined by narrow margins and absolute pressure. Among the jagged rock formations, the muddy trenches, and the sunken ledges, space is the ultimate currency. In this cold, unforgiving world, survival does not belong to the swift. It belongs to the armored, the patient, and the deeply entrenched. This is the domain of the lobster. To understand the lobster, you must understand its relationship with confinement. For this heavily armored crustacean, open water is a death sentence. To be exposed is to be eaten. Therefore, its entire biology and behavioral hardwiring are optimized for backing into the tightest, darkest, most impenetrable crevices it can find. To the lobster, a tight space is not a trap. It is a fortress. Resistance is safety. This deeply ingrained biological mandate is the exact mechanism humans exploit to catch them. And it is also the exact reason why harvesting lobsters is one of the most consistently hazardous occupations on the water. The danger of the lobster does not stem from a venomous strike or an aggressive, predatory malice. It emerges from a brutal mechanical ecosystem where heavy industrial gear, freezing water, unpredictable seas, and a highly defensive wild animal violently intersect. It begins with a trap, commonly known as a lobster pot. The trap is a masterpiece of psychological manipulation rather than brute force. It is a heavy cage, baited with dead fish, featuring funnel-like mesh entrances. It does not force a lobster inside. It invites it. The lobster, sensing the food and feeling the comforting, enclosed geometry of the cage, crawls willingly through the narrow opening. Once inside, the sloping funnels make finding the exit practically impossible. The human hunters have effectively tricked the animal into treating a steel and wire prison as a safe haven. But what works as a quiet, passive trick on the seafloor becomes a massive, kinetic hazard the moment it is pulled toward the surface. The lobster trap is tethered to a buoy by a long, heavy line that stretches vertically through the water column. This simple rope is the first deadly component of a human-lobster intersection. When a commercial fishing vessel pulls alongside the buoy, the line is wrapped around a hydraulic winch. The hauler screams to life, pulling the trap from the bottom at high speed. In rough seas, with the deck pitching and rolling violently, that tension line is a nightmare. It can snap tight unpredictably. It can snag on a fisherman's boot, a loose piece of clothing, or tangled gear. If a man is caught in a line as a trap is thrown back overboard, or as the winch pulls with thousands of pounds of force, the physics are entirely unforgiving. Men have been dragged to the bottom of the sea in the blink of an eye, pulled down by the very gear designed to lift the lobster up. When the pot finally breaks the surface and is swung aboard, the danger shifts from the line to the mass of the cage itself. A commercial lobster pot is not a lightweight basket, saturated with seawater, encrusted with barnacles, thick with kelp, and loaded with catch. It can weigh over 100 pounds. This heavy, dripping, iron and wood cage swings over a deck that is slick with fish slime and ocean spray. Momentum is the enemy here. A swinging pot does not stop easily. When it is slammed down onto the rail of the boat or dragged onto the sorting table, it lands with bone-breaking force. Countless injuries in the lobster fishery have absolutely nothing to do with the animal. They are the result of fingers, toes, and hands being brutally crushed between the unyielding metal bars of the trap and the solid fiberglass gunnels of the pitching boat. It is an industrial accident waiting to happen, fueled by exhaustion and the relentless, hurried pace of the haul. But inside that heavy, dripping cage, the animal is waiting, and it is fully armed. A lobster hauled onto a boat is an animal experiencing profound, terrifying stress. It has been dragged from the dark, quiet bottom, subjected to agonizing changes in pressure, and dumped into blinding, noisy, gravity-heavy world of humans. Its instinctive response to this trauma is not to submit. Its response is to brace, to grip, and to fight. The lobster defends itself with a specialized, asymmetrical arsenal. Its massive claws are not identical. One is a crusher claw, bulbous, heavy, and lined with thick, blunt nodules. It is a hydraulic vise designed to shatter the thick shells of clams, crabs, and sea urchins. The other is a cutter claw, slimmer, faster, and lined with razor-sharp, serrated teeth designed to slice through muscle and tear flesh. When a fisherman reaches into the tight, confined space of the lobster trap to pull the animal out, they are reaching directly into a prepared defense. The lobster naturally braces its legs against the wire mesh of the cage, gaining incredible mechanical leverage. As the hand approaches, the lobster blindly snaps its claws backward. If those claws find human flesh, the penalty is severe. A lobster claw does not gently pinch. It closes with a speed and a compressive force capable of splitting fingernails, tearing deep into the web of the hand, and fracturing the delicate, small bones of the fingers. And because a lobster's defense relies on gripping tightly to prevent predators from pulling it out of its crevice, it refuses to let go. The human instinct when bitten is to forcefully yank the hand away. But yanking only causes the serrated teeth of the cutter claw to saw deeper into the flesh, tearing the skin wide open. The fisherman is locked in a painful, bleeding stalemate with a heavily armored creature that is bracing itself against a 100-pound steel cage. This highly volatile interaction is drastically worsened by the environment in which it takes place. Freezing cold water. Lobsters thrive in frigid marine environments. For the fishermen working the decks in the North Atlantic, the cold is a constant, numbing presence. Thick, rubberized gloves provide some protection against the weather, but they severely limit dexterity and completely dull tactile feedback. After hours of sorting wet gear in the freezing spray, a fisherman's hands become sluggish and numb. This cold-induced numbness creates a terrifying sensory lag. When a fisherman reaches into a pot and a lobster claw closes over their gloved finger, the initial pressure might not register in their frozen nerve endings. Because they don't immediately feel the pain, they don't immediately pull back. They continue to reach or they twist their hand, unwittingly allowing the lobster to secure a perfect, bone-crushing grip. By the time the agonizing realization punches through the cold and reaches the brain, the claw is fully locked. The damage is already done. The numbness turns an avoidable graze into a severe, crushing injury, simply because the environment stripped the human of their early warning system. And the trauma of the lobster boat is rarely a single, dramatic event. It is a slow, cumulative grinding down of the human body. The danger is chronic. Fishermen suffer from a relentless accumulation of minor wounds. A small pinch here, a sliced knuckle there, a scrape against the barnacle-encrusted wire of the pot. In the sterile environment of a modern office, a small cut is an annoyance. On a lobster boat, it is an open door for aggressive marine bacteria. The ocean water, the bait, and the lobsters themselves are teeming with microbes. Those tiny, repetitive cuts become chronically infected, swelling with painful, localized cellulitis. The hands of career lobstermen are a roadmap of scars, thickened skin, and permanently stiffened joints, a testament to a lifetime spent plunging hands into the defensive perimeter of a wild animal. This systemic danger extends below the surface as well, into the perilous world of commercial divers tasked with untangling lost gear or retrieving traps that have wedged themselves into the rocky bottom. For a diver, a lobster trap is a deadly underwater snare. Working at depth, often in freezing water with mere feet of visibility, the diver must navigate around the heavy ropes and the steel cages. The ocean currents pull and push at the lines, threatening to wrap around a diver's air hoses or limbs. If a diver becomes entangled, the heavy pot acts as an anchor, pinning them to the seafloor as their air supply slowly dwindles. And as the diver blindly wrestles with a tangled mesh, attempting to cut themselves free, the lobsters trapped inside the cage react to the commotion. They snap their claws through the wire, striking at the diver's hands. The lobsters are not trying to drown the diver. They are simply reacting to the chaotic vibrations of the struggle, but their defensive snapping add a layer of sharp, painful distraction to an already terrifying life-or-death puzzle, narrowing the diver's margin for survival even further. The story of the lobster is an unparalleled look into the hazards of routine. We culturally view the lobster as the ultimate symbol of culinary luxury, a bright red centerpiece served with melted butter on a pristine white tablecloth. We completely disconnect the meal from the cold, industrial violence required to harvest it. We look for danger in the ocean in the form of massive teeth and aggressive predators. But the lobster proves that danger does not need to hunt you. It does not need venom. It does not even need to be particularly fast. The danger of the lobster is a danger of physics and biology perfectly overlapping. The heavy trap falls with the exact same crushing momentum every single time. The rope tightens with the exact same merciless tension. The claws close with the exact same blind, evolutionary force. The lobster does not adapt its behavior to accommodate the human workflow. It simply reacts to confinement the only way it knows how. When humans become tired, when they become complacent, when they rush the hall to outrun a coming storm, they step out of rhythm with the machinery. And when that happens, the system punishes them. The lobster trap, the winch, the freezing water, and the crushing claws all work together to remind us that we are guests in a profoundly hostile environment. The ocean does not care about our appetite for luxury. It only cares about the rules of pressure, leverage, and survival. And the lobster, backed into its corner, enforces those rules without a single shred of hesitation. The world is full of untold stories, hidden truths, and extreme environments, and we are just scratching the surface. If this journey changed how you see our planet, hit the like button to let us know. Subscribe to Earth's Documentary and ring the bell so you never miss our next deep dive into the unknown. Don't stop exploring now. Click the video on your screen to uncover another extraordinary story right away. We'll see you in the next one.